Hi everyone. Today we are going to learn some of the very basic stuff about MOS transistors. I will specifically talk about MOS because that is what is being widely used. CMOS process, which consists of the NMOS and the PMOS devices as building blocks. They are being widely used to build a variety of circuits from low frequency to high frequencies. All kinds of RF and analog circuits, low voltage, high voltage, everything. Analog, digital, microprocessor, everything is built out of CMOS. So I thought it's good for us to go through some of the fundamentals and understand what are the MOS transistors, how do we operate them, some of the basic fundamental knowledge about it, and eventually extending it to where we can look at some of the simple amplifier circuits and other circuits built out of MOS, and going into like as complex circuits as like operational amplifiers, even looking at that. So to understand all that, first we need to have the fundamentals, the basics. So this set of lectures is actually aimed at doing the basics here. So first let's start with silicon. Okay, and this is something that I read in one of the slides some time back and I found it very interesting. Is if we take different kinds of materials, right, we can break them either as they are conductors. Conductors means they have low resistivity. So if you apply a voltage across it, they have low resistance and they will carry current very quickly. For example, a piece of metal, which is a very good conductor, if you apply a voltage, it's going to carry a lot of current, and hopefully you're not holding that piece of metal, but that's what is a conductor. It has low resistivity, means it could carry a lot of, the current is going to be higher in it. Insulators are the ones which has got very high resistivity. So what they do is if you apply a voltage, they tend to block any current from flowing through them. That is what we call as the properties as high resistivity. And there are many kind of insulators. Like in this particular context, we'll talk about silicon dioxide as an insulator because that is what is being used in making this building up this MOS transistors. So silicon dioxide is an insulator. But you can go back and you just look at, so for example, you're trying to work with some electrical gadgets, you would put some insulating gloves. Those are insulators because it's made up of a material where even if you apply voltage across the material, it's going to block any flow of current, so that's an insulator. So we have a conductor, we have an insulator, and in between we have what we call semiconductors. That's what silicon is. And silicon is the most widely used semiconductor, and we make our MOS devices primarily out of silicon, almost all of it out of silicon. Simple, and that is called semiconductor because it falls in between the two. It's not a very good conductor, it's also not an insulator, so it falls in between the two, and that's where we use it. One of the other reasons we use is this semiconductor. Since it's in between the two, you could actually change its property, and that is what is the main property that's been exploited, to turn it on heavily to act like a conductor, or turn it off so it acts like an insulator. So semiconductor is in between the two, and it is programmable, and we'll see how, where you could make it act like a conductor or like an insulator. Okay, let's look at the silicon crystal structure. Okay, so the silicon atom, and again, I don't have a lot of details here. I'm also not very good at all these fundamentals, but I just want to show you something which will help you understand some of the concepts that we'll talk here. But please go back and refer to, there's a lot of information on the web and the books and all to understand this, the crystal structure of silicon. So silicon has got, the way it forms a crystal is it's like a diamond shaped. Okay, so this is my drawing is not good, as you can see, but if there is a silicon atom, this is a silicon atom, okay, in the middle of this diamond shaped, it actually tries to form bonding with 4 other silicon atoms which are showed at these various respective corners. Okay, so this is an atom. I haven't even talked about how many electrons it has, and also we'll talk about that. So each atom will try to bond with 4 different atoms. Why is it important? Because at the end, this actually gives it different characteristics. This is a pure silicon, a semiconductor. But if I wanted to change its characteristics, what we call N-type or P-type, we'll talk about it more, either trying to make it an N-type conductor or a P-type conductor, then we will do things to it. But before that, we need to understand what the crystal looks like. So here one is bonded with 4. You can take this one and say this is going to bond with 3 more. It's bonding with this one, but there are 3 more. If you extend it, it tends to form something called a diamond cubic lattice structure. it tends to form it. Now each atom actually has got 14, I think its number is 14, it has 14 electrons. And again, you can go back and read through it, that all the electrons which are there and all, but it has got 14 electrons surrounding this atom, right, which constitutes this atom. So this is the silicon structure, but then what we normally use is we don't use p-type, we don't use silicon as such. Silicon is there, like if you take sand is nothing but silicon dioxide. Okay, that's what pretty much sand is, and from the sand you can extract silicon. You take sand and you heat it up to an extremely high temperature, you will break the bonds between silicon and oxygen. Oxygen will go out, and what will be left with you is pure silicon. It will be molten silicon, and then as you cool it slowly, very gradually, you don't do it fast, you do it very, very slow cooling, then it will come back to a structure like that, and you will get pure silicon, okay, as an element. But we don't normally use it. We use either a p-type silicon or an n-type silicon. What does it mean? So first of all, by the definition, p-type silicon is something which is more rich in holes. Okay, and this is a concept which, okay, let's do the n-type silicon first, because it's more easy to understand. N-type silicon is more rich in electrons. What it means is, look at this lattice structure here. What I can do is I can take this pure silicon and I can bombard with impurities. There could be different kinds of impurities, like for n-type I could bombard it, let's say phosphorus, or I can bombard it with arsenic. And if I bombard the silicon with this, what does it do? It does something like this. I couldn't draw it, but I will refer you to a website whose address I think you can see here. But see, this is a silicon structure, right? This is a silicon atom which has got 4 electrons around it. These are the 4, it has got 14 electrons. Each silicon has 14, but it only has 4 electrons at the very outside of those bands. It has got this various bands, right? Some of them which are very closely attached to the center of the core of the atom, but some of them which are not so strongly attached to the core of the atom, and those are, that number here is 4. Okay, so these are the 4 atoms of the silicon, 4 electrons of the silicon atom. Here is another silicon atom, here is another silicon atom. But what you could do is you could actually knock out a silicon atom and replace it with a phosphorus atom. It could be phosphorus or arsenic, one of them. So when you do that, what happens is, let's take this example where it's phosphorus, right? Silicon has 4, but phosphorus actually has 5. So the phosphorus will come in and it will sit in between all the silicon atoms happily with this 4, but what happens to this 5th one? During this process of this phosphorus adapting to its environment, one of its extra electrons just goes out and becomes free. So now what has happened is its lattice structure is same as silicon. You can't really tell whether it was a phosphorus or a silicon. The silicon guys understand, oh, this is also a silicon. So it sits pretty nicely in a silicon lattice, but now it has actually given you an extra electron. So if you get extra electron by bombarding this, say, phosphorus atoms, then that is what we call as an n-type silicon, because it is more rich in electrons. It has more free electron charges, okay, which are there. So this E, wherever I try to use E minus, that's an electron, and a hole I will try to use this. So by bombarding phosphorus or arsenic type of materials into pure silicon lattice, you maintain the structure of it. Oops, sorry, wrong window. Okay, where did that window go now? Okay, here it is. Things are a little crazy sometimes. So by bombarding with the right type of material, you have caused an extra electron, while the other lattice silicon atoms sit happy with the phosphorus and can't really tell a difference with the phosphorus there. So this is called n-type doping, where you dope it, where you push these material into the dopant. These are like highly charged doping that could go on, Now the p-type. Similarly, what happens in a p-type? So p-type, let's take a material like a boron. Okay. So when you dope boron, let's say you're trying to dope boron into the same silicon. Every silicon has 4 of them in the outside band, 4 electrons, and the boron has 3 of them, which is shown here, 1, 2, 3. So if it has 3, one of them, he wants to satisfy this. This is empty, right? So one of the things that could happen is it could remain empty, in which case it acts as a hole. If the electron is not present somewhere, that acts as a hole. A hole is a place where you are trying to attract an electron from somewhere. That's what a hole is. So either it could sit still as a hole, or you could have a neighboring silicon atom which could give out an electron to satisfy this space, but then he himself ends up with a positive. This is like a plus here. It's a plus because it's a hole. A hole is a name which is a superficial name, but it's an empty space. It's an empty space when an electron should have been there but was not there, and that's why you have this electron going out of there and creating an empty space, which is also called as a hole. So this is how we can create an N-type and P-type type materials. Oh boy, now I gotta find where is my... No, that's not the one. Okay, that's the one. Okay, here it is. So as I said, most of the time we will not use the silicon, pure silicon by itself. We will dope it in such a way whether it turns out to be rich in holes, which is a P-type silicon, or rich in electrons, which is an N-type silicon. So holes, always understand that there was an electron, it's void of an electron from there, and that's why it created an empty space, and we call it as a hole. Okay. So now we have seen doping, we have seen silicon lattice and doping, and now with this doping, let's go to the MOS transistor, because this MOS transistor is a building block. That is what we're going to talk about mainly, and how we make different kinds of circuits out of this building block. If you already know BJTs, you can replace BJTs in most cases with a MOS. Most of it is similar and you already know how we use, but if you have not studied BJTs, which are bipolar junction transistors, then this is also good enough. We will go through all the fundamentals and I'll try to teach, share the basic knowledge that I have of all these devices. So first let's do MOS. MOS stands for M is for a metal, O is for oxide. In this case specifically it's silicon dioxide is the oxide, and S is the semiconductor, which is either a P-type or an N-type semiconductor. That's how the name MOS comes in, metal oxide semiconductor. So let's look at, we're going to look at 2 different kinds of MOS transistors are there. One which is more of an N-type, that's why it's called NMOS transistor. One which is a P-type, which is PMOS. So we'll look at it later, but let's look at NMOS. What do we do here? There are many fabrication steps that it goes through, and I think for that I'm not going into all those steps. It will take a long time to explain all the steps, but so please refer to literature, textbooks online and all of MOS fabrication steps. But eventually what we get is we start with a P substrate to make an NMOS. Whatever the MOS you're trying to make, if it's an NMOS, you start with a P substrate. Okay, you start with the opposite one. So there is a substrate. This was a normal silicon which has been now doped, as we explained earlier, to make it more like a P-type silicon. Okay, so this is a P-type silicon here, which I'm calling as P substrate. It is rich in holes. Okay, it has more and more holes, means it has been devoid of electrons. The silicon atoms are devoid, more and more silicon atoms are devoid of electrons. Okay, one thing that I did not mention is, and I think it was over here, is you might have a question of when you dope, how many can you dope? Because see, you're doping impurity, right? If you're doping boron, arsenic, or whatever you're doping, if you dope almost like one impurity per say so many silicon atoms, that's considered kind of weakly doped. Okay, so you've changed the characteristics of the pure silicon to more of a P-type or N-type, but in a weak fashion, because you only have one of these boron atoms, let's say, per 1 billion silicon atoms. That's very, very weak doping. But a strong doping is you could do it a lot of them, where a lot of these silicon atoms, because this is a continuous lattice, if you extend it, you will see many of these places are going to see a lot and lot of borons this way, where it could be almost up to 1,000 silicon atoms. That's a very, very heavy amount of doping. So then it will take it into an extremely P++ type, doping. So it's not silicon anymore. It's like an extremely highly conductive form of silicon caused because of a lot of this doping of the boron atoms. Okay, so that's a doping dose to explain it's weakly doped or it's strongly doped. Okay, now sorry, now getting back to this again, NMOS transistor. So to make an NMOS transistor, you start with a P-type silicon, and this is not a very heavily doped, it has a certain amount of doping. It's more like weakly doped, so it has a high resistivity. Silicon has a high resistivity. By high means it's not so high as insulators, but it's high enough. It's not a conductor. Okay, it will not carry a whole lot of current if you applied a voltage across this guy. So we start with a P substrate, and then eventually we'll make two buckets here called N plus. These are heavily doped now. As we talked about, these are heavily doped with N-type material. So these are very heavy in terms of electrons. So you have P substrate here. This is all P, but here you have got a heavily doped N plus, heavily doped N plus. Okay, and on top of it, with a little overlap, which is always there, we can never avoid it. We grow the silicon dioxide. This is an insulator. So this is an insulator grown on top of the substrate, and on both sides heavily doped N plus regions. And there are 4 terminals that we need to understand of a MOS. This gate, the insulator gate, is called like the gate. Okay, this is what we call the gate. There are 2 dopings. You can call one of them as source, one of them as drain. You can interchange it. Okay, this is a symmetric structure. The one on the left and on the right are the same, so you don't have to specifically call this as the drain all the time or the source all the time. What distinguishes something to be a drain or source is based on what voltage is applied there. So from a semiconductor fabrication point of view, there is no difference. It's symmetrical left and right. But what voltage is applied at the source terminal or what voltage is applied at the drain terminal, that then determines which is the source and which is the gate. Okay, so it's electrically determined. So those are the 3 terminals. The 4th one is called the substrate, also called as the bulk sometimes, so I'm going to call it as a B. A typical way the symbol that is shown for the MOS is, this is a symbol for an NMOS. These 2 are symbols for NMOS, where you can have an arrow, and sometimes in the digital world you don't even draw the arrow, you just leave it like this. So you got a gate, you have the bulk, which is not drawn most of the time in the digital world, you have a drain and a source. Okay, so this is the symbol, because we will use this symbol a lot of times, and if you have already seen this, then that is good, but if you haven't, then let's just these 2 are for the symbols for the NMOS. Coming back to the structure, let's say normally we attach a voltage source between, say, drain and source. Okay, so let's see what is happening. This is heavy in electrons. There's a lot of electrons here, but this is a P-type material. So as you can see, it forms an N plus to P diode. Okay, so there is a diode here, N plus to P diode. This is also an N plus to P. So there are 2 back-to-back diodes here, and the current could only be formed by electrons, because what could flow here, since it's an N-type material, it's heavily rich in electrons. The only thing that could be flowing in and out of the source is are electrons. The only thing that could be flowing in and out of this drain here is electrons. But there is no path. There is no path to connect the 2. The only path is through this P substrate, and this is a P region. If it's a P region, that means it is depleted of electrons. It has less number of electrons present there. So you have got extremely high number of electrons on both sides waiting to cause a transfer from source to drain, but unfortunately in the middle there is no channel. That's what we call as the channel of electrons, and it's kind of off. So there is no path. So even though it's a MOS device, there is no current flow that is going to happen from source to drain, except leakage. We'll talk about leakage later on. So that is the basic structure, okay, of an NMOS transistor. And this NMOS transistor is what we use. It is also called more like a okay, let me not confuse you right at this point. Let's just use that this is the NMOS transistor we're going to talk about from now on. Okay. Now let's go to the PMOS transistor. So what do we do in PMOS? If it's PMOS, we start with the opposite type of material, which is N-well. Okay. So we start with N-well, which is going to be, why am I calling N-well here? Because what you're doing is you want to start with the opposite thing. Because see, if it's let's go back here. If it's an NMOS, and if I had an N-type here, the channel will be there all the time, right? And that is actually one kind of a MOS device, which I didn't want to talk about because we don't use it more. We want to start with something where the channel is off. Here there is no channel, and to make sure that there is no channel from the source to drain, we always start with the opposite type of material. So in NMOS we started with P substrate. For PMOS we're going to start with an N type of material, which I'm calling as an N well. So how do you do it? So the P substrate is common. This is a substrate. These are the wafers that you get. It's a P type wafer. So what you will do is first you will dope a big well region. Okay, like a three-dimensional, like a square type maybe region, or a cube, more like a rectangle or square or whatever it is in three-dimensional, but 2D it will look like a well with N type of material. So it makes it N well. Okay, it's not N plus, it's not heavily doped, but it has got similar properties of resistivity as the P substrate, but in most cases it's actually the resistivity is less. That means this doping is actually more higher compared to the P type doping in the substrate. So we make an N well. So this has got a ton of electrons, it's rich in electrons. Then we are going to make these two tubs, the source and the drain, which will be P plus. So this will be done with P plus type dopants, which will create. So these regions are heavily rich in holes, means they're devoid of electrons. Okay, so these holes, which are empty spaces, right, they are the ones which are trying to attract electrons. And anytime a hole attracts an electron from a different space, guess what, the hole just moved to some other space, right? Because an electron was somewhere, and if you pull that electron to you to cover up your hole, to fill up your hole, you create a hole somewhere else. So in a way, that's how the holes could move and cause conduction of current, because it's the electrons which are moving, which in a way is causing the holes to move the opposite direction. So the direction the electrons move, holes are moving in the opposite direction. So in a way, even though the current is caused by electrons, movement of electrons, it is defined as more like by holes which are not physically moving. But so in a way it's kind of a little confusing, but always understand that holes are the ones where it is devoid of electrons. Okay, that's what a hole is. So here we have got less electrons, right? Here we've got a ton of electrons. So if it's holes and you wanted to cause a current from source to drain by holes, you can't, because this region is off. It is devoid of holes, it's very rich in electrons. So again, you have made a PMOS transistor, right, which is off. It's screaming, give me current, I want to carry current, but you're not able to because of the way the structure is made with an opposite type of material. So we have a P substrate, we have an N well whose tab is here. Again, we call it like a bulk. So it's an N plus to N well. This is a low resistance connection. This is the bulk. Then we have the source and the drain, which are again interchangeable. They are P plus. And then we have the oxide, at which we apply the gate voltage. And this gate voltage, as you might have been thinking by now, is the control voltage, which will turn on and off the channel here. Okay, that's how we're going to start functioning this MOS device. In terms of the notation, you have a PMOS which could have an arrow pointing inside. Look how NMOS is. The NMOS, the arrow points outside. PMOS, the arrow points inside, and it's on the top. Same source, drain, gate, bulk connection. And again, what is source and what is bulk is depending on the value of the potential there, the value of the voltage there, that is what we'll define. From a fabrication standpoint, it's symmetrical. You could swap it, but based on what voltage is attached there, it will change it, and we'll see what I mean by that. In the digital world, you will not have the arrow, but you will actually have a little dot here at the gate. So a dot at the gate means it's a PMOS. No dot at the gate means an NMOS. Okay, so this is predominantly used in the digital world. This is what we mostly use in the analog RF world, but it's up to you. Now you know all of them, so that's what it is. So that is how the MOS transistors are fabricated. But we have seen the MOS transistors which are off. By default, in this case, they are off. And let's see, how is MOS used as a building block? Okay, so these MOS devices are used as a building block. So let's see how do we use them. So I'm showing an NMOS device here. Okay, everything I talk about, it will also be true for PMOS, but it will be the flipped in terms of the type of the voltages will be reversed and the polarities will be reversed. But let's just try to understand the NMOS first. So in NMOS, which is a building block, as I said, if you see what all do we have in these electrical circuits. In these electrical circuits, we have various things which are shown here, and this NMOS block could be used as a current source. This is from drain to source, you could be carrying a current which could act as a current source with the gate acting as a control terminal. Gate could be providing a control voltage. So this NMOS could be used as a current source, which is what we will see. It could also be used as a switch. You could turn it on heavily using this gate in such a way that drain and source are shorted. So you could use it as a switch with low resistance, or could be even with high resistance. In this case, it acts as a resistor, a linear resistor. So you could use the MOSFET also as a linear resistor from drain to source. Again, the control being the gate. The gate is going to be the controlling guy who will determine whether it's a resistor, whether it's a current source, and all that. But most of the time what we will use, and as I've noted here, is MOS is going to be, all these building blocks are used as an amplifier. In the analog world, we use them as amplifiers for both analog as well as RF applications. So in most of the time, most of the cases, we'll be using them as amplifiers. In digital world, we use them mostly as switches. Either the switch is on or off. That's what will be there. But in analog world, mostly as amplifiers. And by amplifier, what do I mean is the gate, if you bias it properly, and as we will see how all these things can amplify. But for now, just physically think of it as if the gate has a little swing, like a sine wave type, an AC signal here. A very small sine wave could come at the gate, then the drain could look, it'll look inverted. We will see gate to drain, there is an inversion, but it would look like it's a much bigger swing. So if you have a small swing here over time, the x-axis is time, and y-axis is the voltage swing over time, a small swing at the gate could result in a large swing at the drain over time, and that is called as an amplification function. Okay, so most of the time we'll use as that, and the gate, as we also mentioned, is used as a control node, a control voltage, or so how, that's what we're going to look at next. And for that, we'll have to understand how this thing really works, how we turn it on and all that, and that's what we're going to get into it next, which is where it gets confusing also, but it also gets interesting, because this is more like dissecting the MOS. You're getting into all the the nitty-gritty details. You're getting your hands dirty to understand that how this device really functions. So again, here I'm showing an NMOS device, right? The source and drain are heavily rich in electrons, but unfortunately the path in between is more like holes. They're devoid of electrons, so you don't really get this continuous conducting path from source to drain. The electrons here would love to flow, but unfortunately they are not able to flow because there are no electrons here. It's a p-type material, p-type substrate as well. So there are two sets of electric fields that we have to look here to understand how this MOS is working. And these two sets of electric fields, the way I will use this nomenclature, some textbooks use, some use different values, but I just said, let's just use this to be consistent in this lecture. EY is an electric field which is applied from gate to bulk or gate to substrate, okay, and it's pointing down. It's pointing down from gate all the way to the substrate. Why is this electric field important? Because remember that if we apply a voltage between gate to substrate, right, in this case, it will create some electric field. This is an insulator. It is not carrying current, but it always has electric field through it. It may not carry current, but it has an electric field. Electric field is important because anytime you have an electric field and you take a free electron and you said, I'm just going to drop it in the electric field. Guess what happens to that free electron? That free electron gets energy from the electric field, right? It's from basic physics. And once it has energy, guess what it's going to do? It's going to start flying. It's going to start moving. The higher the electric field is, the faster that electron will try to move through the electric field. So if I have an electric field down this way, right, from top to bottom, and if I could put an electron here somehow, that guy is going to go zoom from gate to this point here, right? Of course, that will not happen here because there is no free electrons in an insulator. It's highly resistive material, so there are no free electrons there. And we are not doping this thing to give it any free electrons or holes. So it's not going to happen here. But if I could just hold one in my hand and put it there, that's what will happen. It will go very fast. So that is the importance of an electric field, because the electric field, whenever there is voltage applied, there is electric field. That electric field transfers energy to free carriers, free electrons and holes, and they will go boom, zoom. So that electric field we're going to talk about is EY, but there is going to be no zooming related to EY because there are no free electrons there. It's an insulator structure. But this electric field is important, and I'll show you why. The other electric field is, let's say we applied a voltage at drain to source, some voltage. That will cause an electric field from drain to source this way, which we can refer to as EX. And this electric field is going to be important because this is what it's going to call the carriers to zoom through it, and that is what is EX. So we have got two electric fields. The vertical electric field is EY and the horizontal electric field is EX. Let's see what happens because of these two electric fields. Can we cause current? Alright, now this is I was hoping to keep it simple, but it became a very complicated structure. So let me explain step by step what I mean here. Okay, so we have the gate where we are applying some positive voltage called V plus. Okay, let's not worry about the source and drain at this point. Let's not even worry about the EX electric field. Okay, let's just look at if I apply a voltage at the gate. Let's say my bulk or the substrate is grounded. What happens? Let's just look at that scenario only. A voltage at the gate with reference to bulk which is grounded. What happens? Neglecting source and drain. So we know that this is a p-type substrate. It's rich in holes, right? That means even towards this point where I have these electrons drawn, they will be all holes. That's how we are starting with. The whole region here, this whole row will be of holes. It's devoid of electrons. This whole region will be holes, this whole region will be holes, and so on. Okay, that is our starting point. Now as we apply a voltage to it, what does this do? So we have a voltage difference between gate to bulk, right? And this bulk acts as a big resistor because, as I said, when I say big, it's not as big as an insulator, but it has got pretty high resistivity. Okay, and it's not able to carry current. There is no current flowing anywhere. So if this is substrate and there is no flow of current here and neglect any kind of leakage at this point through this big resistor, what will be the potential here right at this edge? You know, this is silicon dioxide, this is silicon, this is what we call as a channel will be formed there, but not there yet. But what will be the potential there? Right at that edge, it will be like 0, right? Because if this is 0, it goes almost to there. So if this point is 0 and this point is some Vg, it creates an electric field which is shown vertically down called as EY, right? Which we talked about. This cannot carry any current because we are saying this is an insulator. And the lattice structure, the way silicon dioxide has, it needs a whole lot more energy than EY to actually move those electrons move. So no movement of electrons, even though an electric field exists here. So if we have an electric field pointing down this way by an arrow, what happens right to this interface here? As we know from physics is, this electric field will actually create an opposite electric field here and the charge will start generating here. Okay, and the charge that will start generating here is going to be electrons. Where do these electrons come from? Let's not worry about where the electrons come from. These electrons, so based on this electric field, right at this interface on the other side of this, it's an insulator, this is the semiconductor, it will actually start forming a conducting channel of electrons, whose formation starts mainly because of EY. And as we said, EX, from drain to source, let's neglect it at this point. So because of the EY, as you apply more and more voltage, more and more charge will start generating here. Okay, thermally some electrons will generate, and also more here it will generate from this guy. Okay, so source, see, this has got extremely high amount of electrons here, right? This also has high number of electrons. This is a reverse bias diode here, the N to P region. But because this electric field, what it does is it helps those electrons to go over that hump. If you have a reverse bias diode, you know, you need a lot of energy for current to be caused or carriers to be moved across a reverse bias junction, right? Reverse bias diode junction. What this EY is doing is, as you can go and look into the detailed physics of it, it's taking electrons from here and it's actually helping them go over that hump, go over that hill. So it's like a hill these electrons have to climb to go from this side to this P substrate, and this EY acts as their friend. It helps them go over that hill, and once it goes over this hill, right, it starts to flow all these electrons. Same thing here, and gets collected. So the electrons, assuming that the drain is at a higher potential compared to source, the electrons will start flowing from the lower potential to the higher potential. So what is EY doing, this vertical field? This vertical field is helping forming a channel here. It's helping forming a channel, and it's helping all these electrons here go over that reverse bias junction and go through it to start creating the current. That's how the channel is formed. So as you apply the gate bias to be higher and higher, you start forming the channel, primarily aided by this vertical electric field. Okay, so now what we have done is we have gone from having an N plus and N plus with no channel in between to having a very thin channel. This only happens for a very thin region right at the interface of silicon dioxide and silicon. Okay, and then as you move away from the channel, guess what happens is this electric field actually loses steam. Okay, it helped right at the interface to a certain extent to form the channel, but after that it is not strong enough, so it cannot create more carriers here. Carriers can't come this way, so it gradually, this is a gradual process. Okay, it's not just electrons here and right at this point boom goes to holes. No, the electron density will decrease and eventually it will return back to a p-type substrate. So it's p-type substrate here, it's all p-type substrate, it's all p-type substrate here. It gradually starts to change from a p-type to a silicon, neutral silicon, then to an n-type and to heavily n-type. Okay, that's how this gradual transition happens, and the forming of the channel is caused because of this EY, the electric field here. So that is the forming of a channel, which is very, very important for you to understand, because that will tell you that you can then correlate later on looking at a device, is the channel going to be formed or not based on the voltages. Okay, so I think we already talked about it, that the EY is the one V gate to bulk. Okay, gate to bulk, and in many cases bulk is shorted to the source. So source and bulk, if they become equal, you will also see the term VGS a lot of times. But really the formation starts by looking at the bulk, and this is a misconception a lot of designers have, is they think that you just look at the voltage from gate to source. No, source doesn't really play a role here so much, as initially the role is played by the bulk. So you really have to apply this potential with respect to the bulk to actually to generate these carriers here. Okay, and in most cases, since the source is shorted to the bulk, we just tend to say VGS all the time. Okay, so the vertical field helps set up an electric field to attract the opposite charges here to start forming a channel and for the current to flow. Okay, what is the effect of this? This horizontal field really doesn't have so much of an effect to form the channel, but once the channel is formed, of course, as you can see, it's going to sweep away these carriers, right? These are like free carriers put in an horizontal field of EX that's going to sweep it. It's going to determine the current and all kinds of stuff. Then it has an effect. Okay, now one thing you should note is I mentioned that EX has an effect more after forming the channel, but this is assuming the channel is long channel, like older day devices, long channel devices where the source and drain were pretty far away. Then EX does not have much of an effect on forming the channel. But nowadays in the submicron technologies, 28 nanometer going to 14 nanometer, these source and drain are only separated by like 14 nanometers, right? That's just too close, and at that point this field also has an effect on turning on and off of the channel. So that's definitely true for long channel, whatever is written, but not true for short channel devices. But we don't need to go into short channel, because to understand the basics, we will stick to long channel devices here, so you can get the fundamental knowledge, and then we'll apply it to short channel, or what are the non-idealities that come. Okay, so as I mentioned, the third point here is once a thin film of electrons is formed, the channel is formed, they're swept across from source to drain, and that's what creates an extremely low resistivity path, okay, based on the density of this channel, how many electrons are there, and that causes the current to flow. So that's how we turn on a channel and how a current is going to flow through it. Let's go into this and try to look at it more from a symbol point of view. So we have the gate, the bulk, and for simplicity in most applications the bulk is shorted to source, so V gate to bulk becomes VGS, gate to source. That is the gate to source voltage, which is primarily used everywhere. We'll use it. Then we have drain to source voltage, which is also important. So gate to source voltage, which is gate to bulk, is instrumental in turning on the channel. When the channel is turned on, the current flow is now determined by drain to source. So we'll use this term drain to source, and IDS is another terminology, which is the current, the drain current. That's the current that's flowing in the channel is IDS. And what does this really look like? What it really looks like is if I plot it this way, and this is again for long channel devices, and again as I mentioned, that is the assumption we'll take in this whole lecture. So if my x-axis is VDS, okay, drain to source voltage. So for now, let's just say source is grounded. Okay, I'm going to increase my drain voltage. That means I'm moving along this axis here. Y-axis is IDS, the current that's flowing from drain to source. Because remember, we are attracting electrons. Which way are the electrons going? Electrons are going from source to drain, right? Electrons were going from low potential to high potential. So which way is the current actually flowing? Current flows opposite to electrons. So it's flowing from drain to source. That's why I have the arrow going down, because current flows this way because the electrons flow upwards. Okay. So a typical plot will look like this. We'll have a region which is called as a linear region. I'm denoting it as region 1, which after a while, after certain VDS value, it will switch over and become more flat, tries to become more flat. This region is what we call as region 2, or also called as saturation region. We'll look at each of these regions in more detail. So we have a linear region, we have a saturation region when the drain voltage is increased significantly higher. And if we kept in going higher, which is where we don't operate these circuits, we operate the circuits far away from these region 3, it would actually start to cause a breakdown. You apply too much of VDS, you have too much of the horizontal electric field, which will just break you down. Okay, you have too much of the field from drain to source, and it will cause a lot of avalanche type breakdowns. That's why I've shown the current going up, but we will never actually be operating in that region, right? So we'll only be talking about these two regions, linear region and saturation region. Now there is a point that I've marked here, which is called VGS minus VT. So you have some VGS value applied, right? So this plot is only for a particular value of VGS applied. Now you may say, hey, I'm going to change the VGS value, maybe a little higher or lower. It will give you another plot like this, a similar plot but a different plot. So for different values of VGS, you're going to have different plots which look just like this, but their values will be different. For example, if VGS was higher, you will have a plot linearly, it will go up to a value maybe here and then become flat like this. So you could have a curve like that for a higher value of VGS. For a lower value of VGS, it would come this way and become flat maybe like this. So for a particular value of VGS, if you did VGS minus VT, this is a superficial point which is close to this measure, where it actually makes a transition from this linear region to the saturation region. Okay, this is not an actual point. This doesn't go like boom, going straight till this point and suddenly changing. No, there's no sudden changes here. This is a gradual change, but you can put a marker there and say that point where it goes through a gradual change is roughly equal to VGS minus VT, where it transitions from one region, the linear region, to the saturation region. And what is this VT? VT is what we call as the threshold voltage of the device. So what is the threshold voltage? Threshold voltage is defined again as a superficial voltage where the channel is formed. Well, the question to ask is, when you say the channel is formed, again the channel is forming gradually. There was no channel, we applied some gate bias and it formed a little channel, we applied more gate bias, it formed more channel. So what is the definition of when is the channel formed? There is really not a definition. In olden days they used to call, if the current is like 1 microampere. Okay, if we can have a 1 microampere current for VGS equal to VDS for a particular device, for a particular WNL, it is a point that we'll call as the VT, or the threshold voltage. So threshold voltage is really not a single voltage. It only gives you a pointer to a range of voltages. So the voltages around VT is where the channel is actually going from being weak to being strong. Okay, so that is what we call as the threshold voltage as VT, and we still use it, but to define. So as you can say, VT is more like a range of voltages, not a specific voltage. And when you do VGS minus VT, which is what we're defining, this also gives a range of, a region here and not a sharp region. That's what I wanted to tell you. So we'll look into these two regions in extensive detail of what happens to the current flow and how these characteristics are formed. Because you might be thinking that, oh man, this is going straight. Why did it just change like that? It doesn't make sense. Well, there's something that happens inside the MOS which we have to understand in the saturation region, why it behaves like this. It doesn't just keep going linearly, like that. Because if it went linearly, guess what will happen? You have a current, you have a voltage. If the slope is constant, it's a resistor then, right? So in region 1 it acts as a resistor, but here it doesn't act as a resistor. It acts almost like a very, very high value of resistance. So let's see what happens. Okay, so first we'll talk about the region 1, which is the active region, as I mentioned. okay, where it acts like a resistor. So here, again, my assumption is always going to be we define a threshold voltage, we are actually above the threshold voltage. So the channel is formed significantly enough. Okay, so VGS is greater than VT, the threshold, kind of the pseudo measure of a threshold voltage. And as we change the VDS here, what is happening is we increase VDS, the electric field here. Now I've swapped the device, so my horizontal and vertical has changed. But again, I will continue to call this vertical electric field now becomes EX, because previously it was the horizontal electric field from drain to source. So the drain to source electric field is EX, right? So if you increase the voltage linearly, the EX increases, which means that it's going to just linearly allow more and more carriers to go through. So what is current? Current is the rate of change of carriers in the channel, right? The rate of flow of electrons in this channel. More and more electrons flow through it, it's a higher current. Less electrons flow through it per unit time, it's lower current. So as you're increasing the voltage, more and more electrons are getting energy now because your energy is higher and they're going faster, right? And not more electrons are getting it. The same number of electrons are getting it, but they're traveling this distance faster, which makes it, a higher current, right? So overall at the end, as we looked at this plot, it's a very, very linear region till it hits here, and if you found a derivative of it, it would look like a pretty linear resistor. So current to voltage, if you did, it's a linear conductor or a linear resistor, whichever way you want to call it. That's the reason why we call it as a linear region or active region. It acts almost like a resistor. And in many applications, if you biased it in such a way that VGS is greater than VT and your VDS is less than this point, VGS minus VT, you would get a linear resistor. And many of the times we use these MOS devices as linear resistors. Okay, so that is the first region, which is the straightforward region. The second region is what is more complicated, okay, which is what we call as the saturation region. And again, VGS is greater than VT. So what happens? So we had a channel. So let's start with the linear region and say we had a channel like this, a pretty nice thin channel, more like this rectangular box, okay, and we had some electric field from drain to source called EX, and we were pulling carriers, and it was acting as a linear resistor. What happens is at that point, as we are increasing the voltage, when the voltage increases beyond this point, and again this is a superficial point, there's a range of voltages around here. When the voltage becomes more than this, what happens is your electric field becomes higher, right? So you have this VDS, so this is voltage VDS, right? And that is related to this electric field based on what the length is, right? So if the length is some L, okay, now I forgot, is the electric field like a derivative of the voltage, or is it an integral of the voltage? I think it used to be like a derivative of the voltage, yeah. So the derivative of this voltage applied across this length of the channel is the electric field, right? So now what is happening is, and again I'm hoping my assumption is correct because I can't check it right now. So we have EX. Now what is happening to EX as we increase this VDS? As we increase this voltage, right, we are increasing VDS here in this side. That means my electric field is increasing. What happens when the electric field increases? The electric field increases, it gives more energy to electrons. This channel has electrons. The electrons are getting more and more energy. But what happens to these electrons if you give them more and more energy? You would think that, hey, they're going to go faster and faster and faster. Well, no. There is a limit to how much of an energy these electrons can have before they go through something called velocity saturation. They saturate. Their velocity will saturate. So if you had a small electric field, you gave it to an electron, it will go through it and it will have some velocity, right? It will go with some speed. Then you gave more electric field to it, it got more energy, it will have even more velocity, and the velocity will keep on increasing as this electric field keeps on increasing. But then at a point it will saturate. Okay, it cannot just go on, and that's just basic physics. So when it hits the velocity saturation effect, that means the electrons can only travel at a certain rate. So remember, what is current? Current is the rate of travel of these electrons. So when the velocity has become almost constant or has maxed out, your current is going to become almost constant. And that is the fundamental reason why this starts to pinch off, it starts to become constant, almost constant, like this line. Ideally you would want this, but it doesn't, but it's almost constant. So this transition of the region from the linear region to the saturation region really happens because of you're asking the electrons to go much more faster than the physical limit, and they suffer a velocity saturation, and they just saturate, and the current becomes constant because there's only so many electrons can go per unit time, and that kind of hits a constant rate, right? Which is this. So I think I have it here. Is the rate of transfer is dq by dt, and that becomes almost constant. Also, certain other things happen when this happens. We call something as the channel tries to get pinched off. So what happens is, due to this excessive electric field, right, as we said, the electrons undergo this velocity saturation. So when the velocity saturation happens, this channel, which was a rectangular channel from source to drain, right, it used to be a rectangle. Now this end of the rectangle starts to get pinched, and it becomes more like this. It becomes more like a triangular region here, where here are all the carriers, right? So all the carriers are here in this red region, but then as they come here, the region is pinched off, and there are only so many carriers that can pass through because this velocity saturation effect that has happened on this. So this is what we call as a pinched off channel, which happens because of this velocity saturation excessive electric field. It doesn't cause a damage. All it's doing is you just now have this effect of EX coming in such a way that it's not going to allow you to have carriers here all the time, because that would make the carriers go faster than the physical limit, and since that cannot happen, it just pinches the channel off to satisfy that. So only so many electrons can pass through this pinched off channel per unit time. That means it is a constant current. Now let's also look at what happens to EX. If I go here, if this was the length L, the voltage VDS was distributed over the whole channel. Okay, that's how this was distributed. Okay, and it had whatever resistance it had. Now what had happened is, as the channel has got pinched off, this is actually the only region where most of this EX actually drops. Okay, so EX first used to be whatever the VDS was, it used to drop across a long channel length, like this whole length, to cause an EX. But now, as it has pinched off, it has actually dropped across a small amount of the length. What that means is this electric field has taken a double beating. First, it has increased because of increase in the VDS. Secondly, since this channel is starting to getting pinched off, and slowly, the length across which this electric field drops has also reduced, which means both those effects, increase in VDS and decrease in this length where the electric field is, the voltage is dropping. The whole VDS drops almost here, causing the electric field to go tremendous. So it's like a positive feedback system. When this pinching off happens, it happens very fast, and it just saturates the carriers very quickly. Boom. And that is the reason why, because this double hammy thing, double effect, it changes very quickly from linear to saturation region, almost trying to go to a constant current value. So I hope this makes sense. I hope I'm able to explain what is going on here. So we still have electric fields EY and EX, but EX is mostly dropping in this region. So this is still a region of low resistivity, right? You have carriers and it's low resistance, but this is a region of high resistance because the velocity has saturated so much that you could only have a constant, almost like constant current going through it, right? And if you do a derivative of this current, how does the current change with respect to voltage? Voltage being VDS. Well, if it was flat, the current does not change at all with voltage, which means it has zero conductance or very high resistance. So in this region, which is the saturation region where we build our amplifiers or current sources, we have a very high resistance from drain to source. So here we have low resistance, here we have high resistance because of pinching off of the channel. So these are the two regions. We'll look more and more into it, that how we put it in the circuitry and all that. Now let's also look at some of the drain current equations in these regions. So how do we define this drain current, which we called IDS? So first we're going to look at linear region. This is the active region. So here IDS, again, I'm not deriving everything here, but I just put the equations because if you go to the industry or in interviews or something that people ask from the industry, this is mostly what you need to know and explain qualitatively that, okay, this is the equation, this is what happens. So The drain current is given as K prime W over L VGS minus VT times VDS minus VDS square by 2. VDS is the drain to source voltage. VT is the threshold voltage that we defined. It's one of the parameters of modeling of the MOS devices when they are modeled. VGS is the gate to source voltage. What is W and L? W and L is the gate. So this is what I'm trying to show, the silicon dioxide gate from the top view. So if I have to look at the top, we know that it has some length. Okay, we know that there is an N plus region here, right? This is the source. This is the drain where there is an N plus region here, and it has some width. This width part is we never captured because we always talked about the length in that 2D picture that we have been looking at. But if you have a top view, it has some width and some length, and that width is W, the length is L. And what is K prime? K prime is a product of mobility of the electron, which is mu n times Cox. Cox is the oxide capacitance. Okay, so it has got a length and a width of the oxide, the gate. And how much is the total oxide capacitance right there, right, of Cox? That is the oxide capacitance is the mu times Cox. Okay, is the K prime there. So this is the mobility, and this is the oxide capacitance of the gate. And this is the equation when we are in the linear region. So we can say, okay, how can I know that in this region it acts almost like a resistor. I want to use it as a linear resistor. How can I find the value of the resistor? So if you assume that VDS is small, then IDS can be given by this K prime W over L VGS minus VT times VDS. So if you do a differentiation of the IDS to VDS, that will give you the conductance. If you take an inverse of it, it will give you the R-on or the resistance. So this MOS, which acts as a linear resistor with an R-on value, that R-on value would be, if you differentiate this, you will get 1 K prime W over L VGS minus VT inverse of this whole thing here. So 1 by 1 over this whole thing. That is how you can actually make a linear resistor. And this will be a very good linear resistor as well as VDS is less. Okay, but when VDS starts to get more, and you start coming, into this region, it will not be a resistor. Then you're actually going from a linear to saturation region. So it's going to be a non-linear resistor. Okay, so here's the drain current and the approximate value of the resistance that you can use, because in all these designs, what you will use is you will use this first order equations like this, and you will use this first order, simple formulas to actually come up with a design. Like what you want to know, what should be my VGS, if I know my VT, what should be my VGS value, what should be W over L values, if I know the mobility and Cox values from W over L. So all that will actually help you do a first order design on paper. And once you do a design on paper, you put it in a simulator, and from there you fine tune it. So you don't go to the simulator directly like all these CAD tools you have, Spice, Cadence tools. You don't put a design there and start playing with arbitrary values. No, you should always use these simple equations to do a first order design, pencil and paper design, using simple hand calculations. And once you have it, then you go to the simulator for fine tuning. Okay, let's talk about the second region, which is the saturation region. Okay, so in the saturation region, what we are doing is we are above this range where VDS is higher, and there the equation that we roughly use is IDS is K prime W over 2L VGS minus VT the whole square times 1 plus lambda VDS. Okay, so we'll go through all of it, but first let's observe this thing. You must have heard that MOS devices are square law devices. If they have long channel length, they're square law devices. Why? Because the drain current is proportional to square of VGS. That's why we call them a square law device. Rest of the terms, K prime, W over L and all, they are all the same as we talked about earlier. What is lambda? Lambda is a measure of channel length modulation. Okay, so when the channel is pinched off, right, when this channel gets pinched off, after that also this electric field, so when the channel is pinched off, and if all the electrons are completely saturated, right, then no matter what your EX is, you will have a constant current. But the current is never constant. It always seems to have a little effect over VDS. So that little effect of VDS, okay, in this pinched off region, which also translates to a slight changes in EX, that is captured by this lambda, which is what we call as the measure of channel length modulation. That is actually giving you the slope how much is the slope of the current changing, even though it's supposed to be flat constant because of the velocity saturation effect. That slope is given by lambda here. Some cases you can also do 1 by VA. VA means the early voltage for a MOS. Early voltage is used in case of BJTs. So how flat this current is in BJTs is much more flatter, and that's why they are much more better current sources and also much more better amplifiers by the BJT transistors. So but here the slope is higher, and you can take the slope, and if you do an inverse of it, it will be like the early voltage of this MOS device. So similar to like the early voltage of the BJTs. Sometimes VGS minus VT, this point is also called V on or VGST. This gives you a measure of whether you're in linear region or in saturation region. Okay, so sometimes we also use that extensively in the design. Now we also said it's going to have very high resistance. You can see that it's not changing. So what is that? You can take this equation here and you can do a derivative of it, right, with respect to VDS, and do an inverse of it. So if you do that, you will come up with this value here, which is kind of proportional to the early voltage or inversely proportional to lambda. So if the lambda is smaller and smaller, that means this value is higher and higher, right? R1 is extremely high, and because of this thing, we get a very high resistance here in this region. Not as high as bipolars are better, but still we get a very high resistance in this region, low resistance here. So here we use it as a resistor, here we use it as a current source, because current sources require that the parallel resistance, which is R1 in this case, or also sometimes called RDS, as we will develop the small signal model, you want those resistance values to be very high. Then it acts more like an ideal current source, right? So this is showing you that this R1 value is high, and that is how we can build ideal current sources. Not ideal, but close to the best we can do in terms of the current sources. So this is how the drain current gets affected by changing the drain to source voltage. But there is another term we will use later on. I thought I'll just put it here, called GM. GM is the same thing, but in a different way. Oh, I should not have this -1 here, sorry. I created a mistake here. So GM is a measure of how is the drain current changing with respect to gate bias. Because the gate, the current is also dependent on the gate bias. If you change the gate bias, this is only for a particular gate bias. For different gate bias, you're going to have many plots, right? All looking similar. So how does it change with the gate bias? That is called GM, or transconductance. Rate of change of the current with the gate bias called transconductance. And ignore this -1 sign. That's a mistake on my part. I'm sorry about that. So if you do a differentiation of that, you will not have 1 by that. It will actually be this. Again, this is a mistake. So K prime W over 2L times V1. So let's say you're trying to do a design of an amplifier where GM is important. You could do a hand calculation and say, I want so much GM, so for that I need so much of a V on, I need so much of a W and L values. These are the things that help do a first order calculation for your initial design, the first cut design that you do on paper before going to the simulator. So I think we have covered most of this region. One last thing that I want to cover here in this is the leakage. So what happens when VGS is less than VT, or the threshold voltage? Okay, that is also sometimes called the leakage mode, and it is specifically more and more true now that we have gone to sub-micrometer and the leakage is extremely high. In this 28 nanometer and 14 nanometer processes, there are devices where you can't really distinguish the difference between on and off. They have a ton of current flowing even if you don't have any gate bias, and that is just pure leakage current. So leakage is a problem. We don't want the current to be, and the reason the leakage is a problem, let's say you made a chip on a phone, and when you turn on the phone, you're trying to use it as an amplifier. You know that it's going to take more current to do some amplification and all that. But then when I turn the phone off, you would like that current to go to 0. You don't want the chip or the NMOS device to be drawing any current from the battery, right? Because otherwise it will simply drain your battery down. And that's what happens is, even if it's off, it is draining your battery down so much that these devices, even though they're very fast, they have got excessive leakage, and they just simply run out the battery of your phone or any other device. And that's why that happens because of leakage. So how does leakage happen here? So the same device, let's see what happens. So we said that VT is the point, a threshold voltage where the channel is formed. But let's say if my VGS was less than VT, well, I should say VGB here rather than VGS, but assume that the source and bulk are shorted again, as we have been assuming. So if it's less than that, we don't have any significant channel. This is a p-type substrate. We're going to have all these holes here, right? It's devoid of electrons. Then how do we get a path from these excessive electrons here on the source side and drain side? How do we get a path? Well, even if there are no electrons in the channel form, some electrons will always be generated by the thermal process. So there is a thermal generation and recombination process that happens in any of these materials. You know, when you're at a particular temperature, some T kelvins, let's say it's a 25 degrees centigrade. 25 degrees centigrade is 298 degree Kelvin, right? So you take that temperature, and corresponding to that, you can find the energy of the that is available to these electrons, right? These electrons are trying to get free from the lattice structure that we talked about, and not all of them will be able to get free, but some of them will still get free and become free electrons just purely because of what the temperature is. So if the temperature is cooler, less electrons will be free. Temperature is higher, more and more electrons will have the energy to get free. So whenever an electron gets free here, right, through this thermal generation and recombination processes, they will be swept. So if the electric field was not there, those electrons will be generated here because thermal process, but then they will also recombine with this hole and they will go away. There won't be any current. But now that there is a voltage applied from source to drain, as soon as they generate, they are swept, boom. They don't get to recombine with these holes. They go straight through it and cause a leakage current. So the thermal process will actually give rise to this leakage current. Okay. So if the temperature was cold, you will have less leakage because there will be less thermal generation of electrons. If the temperature was hot, you will have more leakage. So when these electronic devices get hot, the leakage becomes even more higher. So this leakage is proportional to the temperature in Kelvin, because that is giving you from physics the energy that it's giving to any electron which is kind of bounded to the lattice structure to kind of somehow break free and just be free. And once it's free and this electric field is there, it'll be swept across. It is also proportional to VDS, because what happens is as VDS becomes more and more, especially for the short channel devices, they actually have an effect from drain to source. They will actually aid in lowering the threshold voltage. There is an effect called DIBL, drain induced barrier lowering, without getting into all the physics. But what it does is when the channel length is shorter, this, even without a gate bias, the drain could actually cause a channel to be formed and in an indirect way cause lowering of the threshold voltage. So if the VDS was higher, it will actually cause more and more leakage, because it will help aid these electrons to jump over from here to here. It's not really helping so much with the thermal process, but the electrons want to go over this hump here. There's a reverse bias diode, it wants to go over that hump. This voltage could actually come in here and help them give energy to jump up across that hump, across that hill. Okay, because that's the hill that these carriers are seeing in the reverse bias diode, but it just jumps across. So leakage increases with VDS. And as I already mentioned, the biggest contributor or the biggest killer of this in today's technology is the length. As the lengths are scaling down, right, this VDS is coming more and more here to the aid of this jumping, and this actually goes almost exponentially. So as the channel length scale down, your leakage actually increases exponentially with the channel length almost, and it goes huge, it becomes huge as you have these smaller and smaller channel lengths. So this is a section on leakage, or when the channel is off, and even if it's off, there is still current that could flow because of thermal process of generation and recombination. They get generated, they don't get a time to recombine because this gets swept across this electric field. And also the VDS could have an effect to pull more and more carriers out of here across the reverse bias junction. So that is on the leakage mode. So these are some of the basics on the MOS, and we'll continue on more as we go along. So we've seen this plot, so I thought we will look at these plots again, which is the y-axis is IDS, the drain current, and the x-axis is VDS, the drain to source voltage for this device. And we can just assume that the bulk is tied to ground here to make it simpler. And I have shown you this plot, one of these plots, but now I'm trying to show you three plots. Why? Because this is ID versus VDS. Okay, But the VGS, the gate to source voltage, also is another variable which, if you change it, will affect your drain current. So the drain current that is flowing from drain to source, in this case the NMOS device, it is affected by the drain to source voltage as well as the gate to source voltage. So it has dependency on both. So if you kept your VGS to some value, say VGS2, right, you can think of this plot as the curve previously that I have shown. Then we will get till this region, which is approximately the V on, or VGS2 minus VT. Roughly till this point, we call this point as a mark separating two regions. The region below this, when drain voltages are below this, it becomes in the active region or linear region, it acts as a resistor. And when the voltage goes above it, it tends to enter the saturation region where the current is more flat and it acts as a higher resistance there. Okay, so this is a plot that you get for a particular VGS value, let's say VGS2, as a DC voltage. But if I changed it, let's say if I lowered the gate to source, okay, we will get similar kind of plots where this knee, this turning around point, will happen at VGS1 minus VT. This will be the point. Okay, below which it's a linear region and above it it's a saturation region. If I increase the VGS to say some VGS3, we get a similar plot where the inflection point, the point where it turns around, is going to be VGS3 minus VT here, which is the V on for that particular VGS condition. Okay, so we could actually plot them with various values of VGS, very fine values of VGS, and you would have like lots and lots of plots, hundreds and thousands of plots you could generate like that, okay, for this device. So I just wanted to show you this because I think I mentioned it, but I also wanted to just draw it to ensure that we understand that this drain current, it's a very, very strong function of VGS. By changing VGS, it changes drastically. But when you change VGS, you're going to hold the VDS constant. The VDS will be at some constant value. It could, if you hold it here, it will be in saturation. If you hold it here, then it will be in a linear region. But the point is that no matter whether it's in a linear region or saturation region, it tends to change pretty fast with VGS. So it's a very strong function of VGS. The drain current, when VGS is fixed, it has a fixed value of VGS. It is also a function of VDS, and it's actually a weak function of VDS in the saturation region. So if I only consider the saturation region, it is a weak function. But if I consider actually the linear region here, then it is not a weak function, it's a pretty strong function because there it acts as a resistor. The IDS to VDS relationship defines a resistor, where the MOS is acting as a resistor in this linear region. So as you can see, it is actually the drain current is dependent on two things. And as we have seen previously, you can define certain terms. One is called transconductance that you must have seen in the literature. The other is called RDS or drain to source resistance. Okay, so the transconductance, and these are small signal parameters. I'll explain what is a small signal parameter versus what is a large signal parameter. But let's just go through the definition here first. The transconductance is the derivative of the drain current with respect to VGS. Okay, so you find the slope wherever you are biased for a particular value of VDS. Maybe you are biased here for VDS and saturation, maybe you are here. You can take that point around there. If you find the derivative, that will give you the GM, which is called the transconductance. RDS is the similar thing, except that now you're trying to see what is the derivative of this current with respect to VDS, which is drain to source. And when you do that, you have to define a fixed value of VGS. At what VGS point are you going to do? Are you going to do it for a VGS curve here? Are you doing it for a VGS curve here, here, whichever one? So for a particular value of VGS, you get an RDS, which is a measure of how is this thing changing with VDS, and there is a -1 sign that will give you RDS. If I don't have this -1 sign, then this derivative gives you actually a conductance, which is what we refer to as a GDS. Rather than RDS, it will be GDS. Now since we are here, let me explain a little bit about what is large signal, what is small signal, because I think we're going to spend a lot of time talking about it. And it is also, I found that this is a concept which is not very, the fundamentals of this thing is not very clear to the students. So I want to take some time, even though I have not written down too much in the notes, I will just try to verbally explain it here. Let us say that we were on this plot, the middle one, okay, VGS2. Okay, and let's pick a point somewhere around here. Okay, so that point VGS2 is applied across this, right? Similar to something like here, even though this is an amplifier that I tried to explain. But you have a fixed gate to source voltage, which is VGS2, and you have some drain to source voltage, which could be maybe this value of VDS somewhere here. Okay, so when you have a DC voltage, a fixed voltage VGS and VDS, on top of those, you could have some small perturbations, say in VGS. So if I consider VGS only, I would say, okay, I have a DC voltage, but on top of that, I could have some small perturbation caused by some voltage. Let's not worry about what causes it. And how do I define what is small compared to VGS and what is not? So let's say this VGS value, right? Let's say this example, just take a number. Let's say it was 1 volt. On top of 1 volt, I caused a 1 microvolt change. Well, 1 microvolt is really, really small. So this plot that you see here, right, VGS2 plot, you will have another plot. If it was 1 microvolt more, you will have another plot just like this, but very close to it. It will really not move much if it was 1 microvolt above or 1 microvolt below in the VGS value. You will have, two plots. Let's say this perturbation. So this 1 microvolt compared to 1 volt, that small signal. Let's say it was not 1 microvolt, it was 1 millivolt. It is still a small signal. Okay, so if I increase this, it has a DC voltage of 1 volt, but somehow, for some reason, I changed it to 1.001 volt, which is 1 millivolt more. I would still have another curve which will be very close to it. You won't be able to really tell much of a difference, and it will still be a small signal. There won't be much difference between that curve and this curve. Now, if I said that I have 1 volt, but now I'm going to change it by 100 millivolts, that tends to now become more of a something which is not small signal. Okay, so maybe this is 1 volt and maybe this is 1.1 volt. Let's say VGS3 is 1.1 volt. So now this has made a big change. Okay, so this is the characteristic for 1 volt. This is the characteristic for 1.1 volt. Let's say assume that, and this is the characteristic for 900 millivolts. These changes are called big changes, and that's what we call as large signal changes. So whenever something changes large signal, you know what the characteristic is. The characteristic is defined completely by, whatever you're getting, like this kind of plots. That's a large signal. But if you are biased at a point and you only caused very small perturbations, okay, which are small compared to this value here, that is what we call small signal. So you will see that going forward, there is going to be a lot of stress on small signal, because we assume that this device, let's say if you are only talking about gate to source, it was biased by a DC voltage, say 1 volt VGS, then we will be, and when we use this as an amplifier, we will only cause small perturbations compared to 1 volt, compared to the DC value, and we will use these parameters, which are called small signal parameters. That's why you can see that whenever we take a derivative, the derivative is true only if you are defining a small region. It is not true over a large region, because see, this is a different kind of plot here, right? So it doesn't have the same shape. If it was a straight line, then its derivative will always be constant, but now here it's not going to be constant. So these are what we call small signal parameters. GM is a small signal parameter, RDS is a small signal parameter. We'll develop a small signal model to do it. So it's important to understand that whenever somebody says small signal model, that means if we look at VGS or VDS in this case, something is causing a perturbation which is small compared to the DC values that is already there. Okay, so we talked about VGS. Similarly, we can talk about VDS. Let's say this gate to source, is a constant DC value, and no perturbation happened here. Nothing changed this value at all. Not by a microvolt, not by a nanovolt. But at the drain, when we said that, okay, let's say this VGS2 is the plot, and we are biased somewhere here, okay, at this VDS, something is causing a perturbation, something is causing a change around this point, which is small compared to whatever the DC VDS value is. And by small, I mean, let's say VDS was also, let's say 1 volt, something like 1 microvolt change or 1 millivolt change or 10 millivolt change is a small change around that biasing point. If you changed it big enough, then it tends to become not small signal, but more like a large signal change. So that is an important thing to understand, as what is small signal and what is a large signal. Okay, so these plots, okay, they cover everything. they show you the large signal behavior with VDS as well as with VGS. But if you pinpoint it to a particular point, right, then you could also apply the small signal and you can derive the small signal parameters out of it, which is what we call small signal analysis of the MOS, which is very, very important. And pretty much everywhere you will be using the small signal approximation and the small signal models. And hopefully now you're clear that where we apply small signal models, where we apply large signal models. Small signal models, when the changes are very small compared to the DC biasing values, then it's small signal. But if the changes are huge, then you don't really get accurate results for small signal model. You need to do a large signal model. Okay, so let's try to explain this through an example of an amplifier. I'm kind of jumping straight into an amplifier where we have this NMOS, which is biased at some VGS2. I just tried to keep the same notation, but it's basically some gate bias. Okay, we are using. The bulk is sorted to source, so we'll just call VGS rather than calling VGate to bulk. It has some current IDS flowing, and we have a resistor here. So some of you might know already, but normally in an amplifier there is gain from input to output. Output is the drain here. Input is the gate, so there is going to be some kind of voltage gain, which is what we want to derive, and we want to understand how there is a voltage gain going from the gate to the drain, and how does it act as an amplifier. How does it amplify a signal which is at the gate? Right now there is no signal at the gate. This is only showing the biasing condition. So before getting into that, how this amplifier amplifies signals and all, I thought we will also just do a quick something which is called load line analysis of, we want to know what will be the VDS. We have applied a VGS. This is the ID VDS characteristic for that particular VGS2. Okay, but we want to know what is the VDS. Sometimes simulators can solve it very easily, but we can also solve it by hand. That what is the value of the R that will and where will it be biased? All these values of VDS are possible. So how do we find it? So we find it through something which is called load line. So this is the R. So if R is 0, where the R has the smallest value, what will be the VDS? The VDS will be completely equal to VDD. So this is one extreme point. So if I take the resistor, make it 0, this is where I would be. This is the VGS and this will be the VDS, and that will be the point where I'll be biased. If my R goes to infinity, right, where it can carry almost no current at all, well, actually in this case we have to assume that there is some path for the current to flow. The current actually here, okay, which also could be going through this if it's big enough, is VDD by R. That is the current. Okay, the IDS, as in this case I'm just assuming that this guy is big enough to carry it, but there could be another path for it to carry it if this V output or the VDS was 0. So this is the other point. So one extreme point is VDD by R, another extreme point is VDD, and there we just draw a straight line going through there, which is what we call as the load line, because we know that as the current increases, or whichever way you want to do it, as the current increases, the VDS will decrease. So this is the way where the current is increasing. Or if VDS is increasing, that means current is decreasing, right? Because this is a linear resistor, it's just VDD minus the IR drop gives you this, and that's why we have a load line which goes like that. Wherever it intersects that point for that particular VGS, that is the VDS. That would be the operating condition for that. So that's how you would find the operating condition. And you will have to make sure that before you use this as an amplifier, I guess I should have explained why I'm trying to do all this. I want to make sure this is biased in saturation. We always want to operate in this region where it acts as a big, a high impedance from drain to source. So we want to operate in the saturation region. So we don't want to pick a value of VGS in such a way that, for that VGS and that R, we are in the linear region. Then you're not going to get that much of a gain. We want to ensure that this is biased in saturation, and all the amplifiers, they will always be biased in the saturation region. That is of our primary interest. Okay, so this will give you an idea of how it's going to be biased, what kind of R you can have. You can't have too little of an R, you can't have too much of an R, so both are a problem. So what kind of an optimal R you can get. But let's come back to the amplifier and do the small signal model. That is what I've been trying to explain, but I think this load line was a little distraction away from it. So let's come back to the same amplifier. So I mentioned this earlier that, okay, this amplifier is biased with a DC voltage of VGS2. okay, some VGS constant value. But let's say on top of that there was a little perturbation, there was a little AC signal, like a sine wave signal, okay, of a very small magnitude. And what by small I mean is this magnitude of this V in is actually smaller than this. For example, if this is 1 volt, this could be a microvolt, millivolt, 10 millivolts, but if it starts getting 100 millivolt, when this is 1 volt, that ratio is only 1 to 10, then it's not such a small signal anymore. So all the small signal analysis is not going to be so accurate anymore. Okay, so if you have a small perturbation at the input, which is the gate, we know that, and in this case the source and the bulk are shorted together, there is going to be an amplification, which is what the small signal model will tell us, that how much it is. So signal here at the gate would get amplified by the time it goes to the drain. The question is, how does it go to the drain and how it does that? Okay, and what will be the output? So that is what we will try to work out to the small signal model. And we will assume that we have picked an R in such a case that VDS is in saturation. So if we had this, right, you have VGS2, you have this ID VDS plot, you know this is biased here VDS, and you know this guy is in saturation. This plot will not tell us what the gain is. It's not that straightforward. You can do it, but it gets complicated from this plot to figure out what is my voltage gain from input to output. To find that, that's when we go to the MOS small signal model. We generate this model, and let me explain this model because we will be using this over and over again, and by the end of this course you should have it in your head where you don't have to draw this model. You should be able to quickly just say, oh, I know this is where the signal is, this is how much the current is, this is how much the voltage is, and boom, here's the gain. You should be able to kind of come to that point. Of course, a lot of it depends on me too, if I can explain it in the right way to you or not. So we already talked about earlier, the drain current, we know is proportional to VGS and VDS, okay? So if these are the small signal values, then it has a proportionality to both of them, and we have seen previously. Shown here is the small signal model, and how does it really come? So you can say that the drain current, as we have defined earlier, is GM gives you the derivative of the drain current with VGS. So if there was a small change in the gate, okay, the drain current will change. Let's say if the gate increased slightly, just a small amount, we know the drain current will increase. This time GM times VGS gives you the increase in the drain current because of the VGS term. Okay, so it's directly proportional, and that term comes to be this. GM being the term which is telling you that, okay, if VGS increased, GM times VGS is how linearly this drain current will increase. It will increase linearly because it's a small signal variation. It's not a large signal variation we are talking. We are developing a small signal model. We also know that if VGS was constant, and if we increase the current in the drain, right? If the VGS was constant and I increased VDS, we also know the current will increase. And that part is given by this term, which is VDS by some RDS. Or you can also call GDS. In many cases we write it as GDS times this. So we have seen this term before, GM. We have seen this term RDS before, which we defined it right here, I guess, yeah. So GM is the derivative with respect to VGS at a particular VDS point. Okay, so this is defined around a point when the perturbation is small. RDS also is defined this way, which is with respect to VDS. Okay, so if we have those two terms, then we can say the drain current is going to have one component, which is GM times VGS, which gives you the VGS dependency and the VDS dependency. Both of them will cause a linear increase. And small signal, what happens is you can, since it's a linear model and there are two guys causing a change, you can just add them up. Okay, so we have the component because of the drain here, we have the component because of the gate, and eventually it becomes an addition of the two, and that leads us to this small signal, simple small signal model, which is what you would be using for pretty much 99% of all your circuits. You will be using this model to find whatever small signal parameter, gain or RDS, output impedance or current, whatever it is. So since it's an insulator, right, the input, so this is the gate terminal, this is the drain terminal, this is the source terminal. Bulk is gone because in this particular application, as well as in most of them, the bulk is shorted to source. So I'm not showing the bulk. But if the bulk is there, you have to consider there's a fourth terminal, and this simple model gets a little more complicated because of fourth terminal. But we will not go there. For learning purposes, first let's do this model. Okay, so Here is the gate to source. Now when we do a small signal model, one of the things we do is we define certain things called AC ground. For example, this is a DC voltage. If the DC voltage is not changing and it's an ideal voltage source, what is its impedance? 0 ohms. A voltage source has an ideal voltage source has 0 ohm impedance. So we will short this and make it AC ground. So this is ground here, but this point will also become ground as AC ground because this is a fixed value that is not changing. What is changing is V in. So we'll keep that in the model while we go for it. So the source is ground, which is also AC ground. If you apply a voltage VGS, which is our small signal perturbation, which as per this model VGS will be equal to V in. Any V in we apply with this point being AC ground will be applied directly across VGS. And I think I have it in the next page, but first let's just go through the model. So if you have any VGS, that will cause a voltage controlled current source here, which is GM VGS. That pulls the current through the drain. Okay, so that's one component, which is here. So any VGS causes a dependent current source, which is GM times VGS, flowing from the drain to the source. Okay, so that's the first component, which is based on the gate perturbations, this term here. The second term is if let's say if there was no VGS, if VGS, the small perturbation was 0, we don't have this current source, it will be open. But we will still have some current because as the voltage changes in the drain to source also, we are going to see some change, in the current here, right? And that is given by RDS or GDS. So this second term here gives you the second current. So if you say ID, what is the ID? It's a summation of two currents, the one flowing through RDS and the one which is GM times VGS. So this model, you can map it simply into this by making a simple small signal model like this, and that's what we call as a small signal model. So we're going to use this again and again. And let's see some of the ways how. So in this model, what all do we need to find? We only need to find two things: GM and RDS. This is our starting point, the simplified model. We are not going to the complex model yet. We will go there, but to see the simplified model, what are the things we need to find out? GM and RDS. How do we calculate it? We can do simple hand calculations first to find what are these values, and that is what we're going to do here. So IDS is the large signal current. So let's forget it for a minute, because remember, this is eventually going to be a subset of this plot. This is a large signal model. This is always true. From here, at a particular biasing condition level, we are deriving a simple model, which is a small signal model, right? So to find this value of GM and RDS, we start from the main source, which is the large signal model, which is current equation when it's biased in saturation. So it will be K prime W over 2L VGS minus VT the whole square 1 plus lambda VDS. This is the drain current equation that we have seen previously. Now to find GM, you will take this excuse me, and do a derivative with respect to VGS, and also make the assumption that this lambda is small for now. Okay, so the modulation effect is small. If you do that approximation, you will get GM as K prime W over L. This 2 will cancel, and VGS minus VT. This could also be rearranged or written approximately as 2 times IDS, the same current. Okay, this whole equation, 2 times of this divided by VGS minus VT. And this is a very simple equation we use all the time, which is 2 times IDS by V on, or VGST, or VGS minus VT. So GM is 2 times the bias current divided by V on. Bias current is what we are already saying that, okay, this device, we know what the bias current is, and based on that bias current, we can directly approximate what the GM is based on the bias current, the DC current without any perturbations from the large signal value, and V on. V on typically in design, in most of the cases, you try to keep it as about 200 millivolts, or maybe a little less, or maybe a little more. But if I go with what is the rule of thumb, where most designers will keep it 200 millivolts, if you put 200 millivolts here, it will come around and it will basically give you a value of 10. So GM would be approximately 10 times that bias current. So what that means is, if you said, hey, I want a GM of 10 millisiemens, I do a rough calculation and I find out that I want a GM of 10 millisiemens, which tells you that the bias current that you will need will be roughly 1 milliampere. So if you had a 1 milliampere, you will get somewhere around 10 millisiemens, maybe a little bit more, or a little bit less, but that is a good rule of thumb or a starting number to do some quick calculations to come up with, if I need some X amount of GM, how much bias current we will need. So typically this range goes from 10 to 20. When you hit 20, you are actually operating the device with extremely low Vons, almost like maybe a few tenths of millivolts. And what that means is your VGS is equal to VT. That means you are in weak inversion. You're not really following all these rules, which is fine. A lot of the designs are done like that, where VGS minus VT is very small, and that is done to get the maximum GM out of the bias current by just making the device fatter and fatter, bigger and bigger, where W over L is just a larger ratio number. So typically the range, just remember this, the GM, the max it could go to is almost 20, okay, and with a very big device, 20 times the IDS. But lower end, 10 times is a good number, which will be corresponding to a Von of about 200 millivolts. That means here this point, this inflection point, which is VGS minus VT, would be about 200 millivolts here. Okay, so that's how we find GM. RDS is found the same way. It's similar formula. If you do a derivative and everything, you will see 1 by lambda IDS. So if you know lambda, you know the bias current, you know what the RDS is. Sometimes you might also know what the early voltage is. Like so MOS devices don't have an early voltage. I have been mentioning it, but it is more like a pseudo early voltage, like what the bipolar devices have. Sometimes people might say, okay, hey, this is a MOS device and its early voltage of say 10 volts, rather than specifying the lambda. So if the early voltage is specified, just V by IDS, the bias current gives you the RDS, or 1 by lambda if lambda is given. So this is how, from the biasing conditions, from what is the bias current, what is the V on, okay, what is the lambda, from there we can find GM and RDS, and once you have found it, you can plug it in this model. Your model is ready, right? The simplified model is ready, and with that, then we can go and find the amplifier gain. So how do we find it? So again, coming back to it, as we said, we have a small perturbation. Any DC voltages like VGS2, this acts as an AC ground, so you can put a ground here. This VDD acts as an AC ground. This is also a DC voltage which is not changing. So this is 0 ohms to ground, so you can put a ground there. So here is my VGS, here is GM times VGS, right? And here is the RDS. This point is my source, or also the bulk. What is connected at the gate to ground is Vin. Drain is my output. What is connected at this point? We have a resistance to AC ground. Okay, so output is here. We have a resistance R to AC ground, so you can put an AC ground here. That's why there is an AC ground. And we want to know, this is the output voltage V out, this is the input voltage V in. What is V out by V in, right? That is the voltage gain. So if I applied a small perturbation, a small signal here, some sinusoidal signal, we are talking about it will get gained up, but how much? So we can calculate it based on the small signal model. So how do we do it? Let's first see what is VGS. VGS is equal to V in. So what is going to be this current? This current is going to be GM times V in, right? VGS is V in. Now, since this point is ground, this point is ground, you can short these two. So we have two resistors in parallel. RDS parallel to R. Whatever the effective value of this resistor is, that is the resistor through which this current GM VGS is going to flow. This is going to flow this way, right? And if you combine these two resistance into a single resistor, it will be flowing out of that resistor and going through this current source, right? So the voltage drop here would actually have a negative sign because it's not flowing into the load, it's flowing out of the load and into this controlled current source. So what is the total effective value of the resistor? As we said, RDS times R. So the output voltage is that effective resistance multiplied by the current. Since the current is flowing the opposite way, it's not going into the load, away from the load into this current source, we put a minus sign, and GM times VGS. So that is the current. This is the load resistor, and if you just rearrange it, put the VGS here as V in, V out is here, we get a value which is minus GM times, okay, whatever GM is, RDS parallel to R. So remember, we can go back and we say, hey, we calculated this is the value of the GM based on the bias current. We had this RDS, so we know the value of RDS. We also have a value of the R, which was based on the load line, but you might be just given the R itself as like, okay, this is the value of the R and this is the value of the bias current. So you plug all these values and it will give you the voltage gain of this amplifier. So this is an example where we went from the large signal characteristics, which are always true, but these will not give you that voltage gain of this amplifier that we were trying to calculate readily. If we derive from this large signal characteristics, if you take a small slice of it at some point, you develop this model, which is called the small signal model, and from here then you go and calculate the gain. Now again, one thing you have to understand is, as we said, V in, it's a small perturbation compared to VGS2, that's also true. But let's say somehow this product became 1000 or 100, 1000 might be too big. So let's say we have VGS2 as 1 volt, V in as 1 millivolt. Okay, so this is very, very small compared to this. But if the gain was big, okay, we said a 1 millivolt is becoming 100 millivolt here. I said the gain is 100 from this calculation. Then what will happen is you're going to have 100 millivolt swing on this VDS. So you have a DC value of the VDS, and around there it's going to swing plus 100 millivolts more or minus 100 millivolts less. When you swing that much, right, and if it becomes a large enough swing, it may not be an exactly correct answer for the gain. Okay, but it will give you an approximate value. So the small signal approximation, is it satisfied at the input? Yes. We say it's 1 millivolt compared to 1 volt. Great, this is small signal here. But the output may not be small signal if we say this gain value was 100. That might be actually causing a 100 millivolt swing here, which may not then be satisfying the small signal criteria that we're saying. This signal is not small anymore compared to the DC value of the VDS, whatever we had. Okay, so you have to keep an eye that all the small signal analysis are correct till the small signal does not remain small signal anymore. If they tend to become large, they would still be correct. They may not be 100% accurate, they might be 90% accurate, but still it's fine. For initial paper, and pencil calculation, for initial hand calculations, it's just perfectly fine. Because after you do all this, you put it in the simulator, and the simulator solve it accurately for you. Okay, so you don't have to worry about it. But at least for us, we need simple models, simple ways to understand intuitively what's going on. So this is this hopefully explains the whole concept of large signal and small signal. So we looked at this example of the amplifier and we developed the small signal model. So I thought, why don't we kind of look at some of the cases where we can actually simplify it further. And actually what happens is, as you get more and more used to these small signal models and the various circuits, which we'll talk about, you will see that in many of these cases we can actually neglect the RDS. Okay, it is not necessarily true in this submicron technologies where the RDS values are very low. That is, the lambda values that we talked about are higher, the equivalent early voltages are lower, so the RDS value is not so high. But at least for doing some initial hand calculations, for a simple understanding of the circuit, or to come up with a first cut design, in most cases we can neglect RDS and actually try to come up with a quick way of analyzing the circuitry without drawing a very, very complicated small signal model. Remember, this model is for only one transistor. So rather than one, let's say if it had 4 transistors, hooked up in a different, some kind of a configuration. Drawing 4 of them, interconnected to each other could be problematic. And even solving them mathematically could be problematic. So in many cases we can make an assumption of simplifying RDS, and that just becomes a simple model like this. You have the 3 terminals, the gate, drain, and the source. If you have a VGS, a voltage across gate and source, you have a current which is dependent on that VGS. So it's a controlled current source, GM times VGS. So if we have this simple model in our head, where we have neglected RDS, it could actually help us do some very quick thinking. For example, I have this thing here, and again I have a single MOS transistor. At its gate we have a V in applied where the source is grounded. So what is VGS? VGS is same as V in. Then we can quickly draw the current growing here is GM times V in. It's GM times VGS. We are not worrying about RDS, and that's a simplification we made. Now what is connected on the top at the drain? Maybe it's some other transistor or something else connected. I'm not going into what that could be, but if I look at a single device, I could use the simple model to go from a voltage to a current. Similarly, you might see other configurations. These are called common gate type amplifiers. I'm sorry, common source. This is common source where the source is at ground. This is a common gate where the gate is at ground. Okay, and we'll look into these amplifiers more, but just to give you the topology, you could have this where the gate is actually attached to a DC voltage. It is biased to some DC voltage, which is AC ground. Now if I applied the V into the source, you know what does it do? Well, again the VGS right now becomes minus V in. Right, this point is ground, this is V in, so the VGS becomes minus V in. So in our small signal model, which says GM times VGS, the current comes this way. Now what happens? The current goes the other way because it's minus V in. So the current becomes GM times V in. So if I applied a voltage here, it will cause a current to go up that way. This also assumes there is an AC ground here, but I just wanted to illustrate this, that if we have a very simple small signal model like this, which has simple 3 terminals and just a controlled current source, then you can pick devices in each and every part of a circuitry. It might consist of 10 transistors, it could consist of 20 transistors, and you could actually go step by step and say, oh, at this point I have this voltage, so this is the current flowing through the device. Okay, and that's very helpful, as we will see when we get into big circuits like op amps and all that. This kind of simplification of knowing what the voltage at one point would be and then correspondingly what would be the current, that helps a lot. So I just wanted to introduce this concept a little bit so that it'll get you guys thinking a little of how I can quickly go from, if I know the voltage applied, what is the current, which way the current is going, and what's the magnitude of the current. Okay, so following on with this, let's also do something which is kind of along the lines of how we can use the simple small signal model that is given here, and derive some impedances. Now one thing I think I forgot to mention is that this is only a DC only model. You can see there are no capacitors here. If you have seen the literature, the model is actually much more complicated with a lot of different kinds of capacitances, parasitic capacitances that come around, and I have not put any one of them yet because that is the next step. We will go to the next step of the model, but first let us just simply try to understand the DC model, what happens during DC wise or low frequency wise, where we don't have to worry about this high frequency type effects, capacitors that come. So this is more of a low frequency model. Okay, so let's see how we can find. Sometimes we have to also in the circuitry, when you do an amplifier, you deal with voltages and currents, you deal with gains, but you also have to many times find out impedances. Okay, so deriving impedances, DC, I said DC, but it should be more like DC and low frequency only, because we are not going to consider any of the parasitic capacitance effects yet. Okay, we will assume that those don't cause any problems in the low frequencies that we are going to be deriving these for. So deriving impedances, let's say we could have a circuitry which we just saw. This is where the gate is common, so it's more like a common gate stage. And at this source point, if I asked you what is the impedance looking here, can you tell me the impedance looking at this point? Okay, just the impedance. Even though I'm calling it a Z in, it is more going to be like R in. Z is an impedance which kind of tells you that, hey, this has a real part and it also has an imaginary part. But as I showed you earlier, we are not considering any capacitances. So this there is going to be no imaginary part, only the real part of the impedance. So it will mostly be more of resistances. This will come out to be more like an R in rather than a Z in. But I'm still just use the word Z in here, and we will use the word Z in again later on in the later lectures. So here you will see mostly the real part of the impedance. But what is the impedance of a stage like that? So your gate is biased at some DC value, which means it's AC ground. Now to find the impedance looking up the source, what you will do is you will apply a superficial voltage source called some Vx, and you want to know what will be the Ix going through it. So if this is kind of an imaginary voltage source of some value Vx and you have Ix, then Z in will be given as Vx by Ix. That's how you find impedance. And I hope that you already know this thing, that how you find the impedance, but if you don't, it's still okay. Anytime somebody asks you to find impedance looking into a particular point, what you do is you just simply put an extra voltage source, which really does not exist in the circuitry, but you just stick in a voltage source of some value Vx, and you want to know what is the current Ix flowing through it. Then that Vx by Ix will give you the impedance. That's how we calculate impedances in any of the circuit configurations. So here in this configuration, if I applied a voltage Vx, what is Vgs? Vgs is minus Vx. So this will start carrying a current which will not come down but more up, and that would be Gm times Vx. Gm times Vgs. Vgs is minus Vx. That's why I changed the polarity or the direction of the current, going up rather than down, and this becomes the current. So this current is same as Ix. So now if you do Vx by Ix, it becomes Vx by Id, and that is nothing but Gm times Vx. Right? So if those two will cancel, and you will see that the impedance of this looking up at the source is actually 1 over Gm. This is a very, very important. You will see this kind of a circuitry in a lot of places as we go forward, where the impedance looking into the source of an NMOS is a low impedance, which is roughly 1 over Gm. Here we assume that the drain is kind of low impedance or AC ground. Okay, that is an assumption, which is what would be true in most of the circuitry. So the impedance looking up into a source is 1 over Gm, which is a low impedance node, and we use it all the time, as we will see in the circuitries, as to actually create low impedance points. Okay, so this is an example of what would be the impedance looking up a source when the gate is AC grounded. AC ground means fixed DC bias, which does not change. That's why it's AC ground. The second example here is simple, where I said, okay, I have the gate at a fixed DC bias, the source is at ground, and rather than asking you to find the impedance looking up the source, tell me the impedance looking down the drain. What is the Z in there? Well, this is a very simple case, because here, what is the VGS? There is no VGS. The gate is fixed AC DC bias, the source is fixed, so the VGS is 0. So if VGS is 0, there is no current source, controlled current source flowing through it. So all you see here is just the resistor RDS. That is the only impedance you will see at looking at the drain. And so this is a case where a MOSFET does not have any gate to source. It only has a low frequency signal applied at the drain, and that impedance looking down then will be simply RDS. Okay, so this is another simple example. I'm trying to show you little pieces here which you can get yourself familiarized with, because later on when we build big circuits, all these concepts will be used there. The last one I have is probably a little more advanced at this stage, but still I thought, why not go through it and derive this case, which is called as a cascode. Cascoding is a concept that is used widely in analog circuits, and it is mainly used to boost the output impedance, especially for current sources. If you have a current source and you're trying to generate a current source, which we will see in some circuits later on, you want the output impedance of the current source to be extremely high, to be infinity as possible. That's how it becomes ideal. So to do that, we also do something called cascoding. Cascoding is basically you have one device whose drain then goes in series with another MOS device. So when you have two MOS devices in series like this, that means they are cascoded. Okay, so this configuration is called cascoding. The gate is going to be attached to two different DC potentials. For example, the gate of the first one is, say, some VDC1. This is some VDC2. So these both the gates are AC grounds. Okay, this source is grounded here, and this is the final output at this point. So you have two series MOS transistors attached. This is the final output, and I've asked this question to a lot of guys. And the first answer they come up with is, if I tell you, what is the Z in looking down here? Can you tell me the impedance? When both of them are AC ground, they will say, oh, there is no VGS. There is no VGS here, which is not true. There is a VGS, we will see that. So since two of the transistors are in series, this is some RDS2, this is RDS1, so the impedance looking down will be RDS2 plus RDS1. It's just like saying two resistors in series. You know, at first that is how it looks like, but that's not the case. You will see it's much more complicated than that. And let's go through this exercise here. That how this impedance looking down is not RDS2 plus RDS1. It's much more than that. So let's look at this case here. So you know, you can see that this definitely has no VGS. The gate is at a DC voltage, which means it's AC ground, and this is a ground. So the way to model this first transistor is simple. There is no VGS, there is no controlled current source. GM times VGS is going to be 0. So this M1 can simply be modeled by a resistor RDS1. That's all you have here. Okay, so this is modeled simply by an RDS1. That is all is the modeling for this M1. Now let's look at M2. At first, if you look at it, you say, okay, the gate is at AC ground, but then we miss the source. The source is actually not at AC ground. It's in between these two, and that could be something, but it doesn't have to be AC ground necessarily, because there is no DC voltage applied here, or I have not attached it to ground. Right? So this is a floating node. This is not an AC ground. So there is going to be some VGS there, and that is the part that most kids tend to miss. They think that this is also VGS of 0, so they have two RDSs in series. No, that's not the case. So let's see how we will model this one. For this, we will have to assume a voltage here, some voltage V1. Remember, we are trying to find impedance. So to find an impedance, you will attach a superficial, an extra voltage source called Vx, and you want to know what is the Ix coming out of there. Vx by Ix will give you Z. Okay, so this is what we are attaching. But we are calling this node voltage as some voltage V1. You could call it any name you want. Why? This is a variable. We don't know what this voltage is when we will solve for it. Okay. So if this voltage is V1, the gate of this device is AC ground. This voltage is V1. So what is VGS of this device? VGS of this device is minus V1. Right? We are talking VGS. So if this VGS is minus V1, what happens to the current? The current actually goes the other way. It goes from bottom to top, right? It doesn't come down because VGS is negative. So here you can see that I have drawn this VGS as V1 with positive and negative here. So the current goes GM times VGS will actually be GM2 times V1. That's going this way. And also in parallel we have RDS2. That is the RDS of this device. So we have this guy here which completes the model of this second transistor M2, and then finally this is the output where you have the current Ix flowing because we have a Vx attached there. We want to know what is the Ix, and so we will know what is the impedance coming this way. So how do we start solving this circuit? See, it's a two transistor circuit, but it's still actually much more simpler than many other small signal models you might see for different circuits. So if Ix flows this way, the Ix will split into two parts. One part is this, right, GM2V1, and the other part is RDS2. But still, whatever goes into these two parts comes out here. There is no other way for it to go. This is open circuit here. This is high impedance, right? So Ix current here, even though it splits into two parts here, all of it comes out here and flows this way. So the first equation we can write is V1 is Ix times RDS1. Okay, so V is equal to IR. That's the first equation we wrote. The second equation we will write is Ix. Now let's look at Ix, which splits into two parts. So Ix is equal to minus of GM2 times V1 because it's going this way, right? So if I were to turn it around this way to add these two currents, I'll have to write minus GM2 times V1. That is this current here. What is the current here in this branch? That branch is, the voltage here is Vx, the voltage here is V1. So Vx minus V1 by RDS2. That is the current in this branch. So Ix coming, splitting into two parts. We have the two parts here. Now what you do is you take V1 and you substitute by this, okay, wherever you can, Ix, RDX1. So here V1 I've substituted as RDS1 times Ix. Here Vx by RDS2 I've kept it as it is, minus V1. V1 again is Ix RDS1 by RDS2. Now take all the Ix terms and move them on this side. So if you do that, it will become 1 plus GM2 RDS1, which is here, plus this term is RDS1 by RDS2. So all that clubbed together for Ix. And on the other side of the equality is just this term remaining, Vx by RDS2. Okay. Oh, it got cut in the bottom. So now if I do Vx by Ix, which is Zn, which is the impedance that we're trying to do, you can do all this math here and finally you will end up with this expression. So this will be a product of RDS1 and RDS2, which is the first guess a lot of students have made to me earlier is RDS1 and RDS2. Of course that is there, but since this V1 voltage is not AC ground, that actually gives you this massive term here. Look at this. GM2 RDS2 RDS1. Okay, so the impedance looking down is RDS2 plus RDS1, but also the product of GM2, RDS2 and RDS1. And most of the time the product of GM times RDS, anytime you see GM times RDS, they are big values. They could be values in the order of hundreds if it's long channel devices, which or if you go to extremely short channel devices, they would still be around 10 or 20 at least. You would be able to get them. Okay, so that value is always much bigger than 1. So anytime you see a product of GM times RDS, it tends up being a much bigger value. So what you can do is you can simplify this and make an assumption that since this is going to be the dominant term compared to any of these two, it roughly becomes GM times RDS1. So what we have gotten here is, if you had a single device M1, the impedance looking down will be simply RDS1, which is what we have here, right? So if I have a single device whose gate is also at AC ground, the impedance is simply RDS. But if I put another device in series with it, which is this M2, so I have the same M1 here, which is same as this, but I put a device M2 in series with it, that actually helped boost this impedance by a significant amount. By how much? By the gain of the second stage. Typically this GM times RDS product is the gain of a particular stage, voltage gain, as we have kind of seen previously. So putting another stage in series with the original device helps boost the output impedance almost by the gain of this extra stage that we are putting in. So GM2 times RDS2 times RDS1 becomes the output impedance, which is huge, which is what you want to see. And as we will see for current sources, when you design current sources, you want the output impedance to be extremely high. And this way, by cascoding, you get that. I had another important thing here, but I'll try to just talk through it because somehow during scanning it got cut. So one benefit you got from cascoding is definitely you have a huge output impedance, which is the first thing you want. The second thing is, what is this voltage V1, okay, as compared to Vx? So let's say we have a Vx, this is moving, right? This Vx value is moving. How much of that movement actually comes across at V1? So you have these expressions. From here you can actually derive that what is V1 divided by Vx. Okay, so you can start with this expression here and you can say V1 is Ix. What is Ix? Ix is Vx by Zn, right? Zn being this big value. So this value Ix will be Vx divided by this huge term here, and then RDS1. So RDS1 and this RDS1 will cancel, and eventually you will see you will be left with this term called GM2 RDS2, which is what is written here. Unfortunately, it's cut during the scanning part of it. So what this is saying is, so GM2 times RDS2 here, which is this term here, is actually the gain of this MOS device. Okay. So if you have a voltage Vx here at the output, V1 will be Vx divided by the gain of this M2. Okay, so it is heavily attenuated by the time it comes here. And that is actually what you try to do when you make a current source. Like when you put a constant bias here, this is creating a current. So this is more like a current source. You have a DC voltage here, and this generates some current for you, DC current. You want that current source to be extremely, a stable, extremely, constant value. Whatever the value is, if it's a 1 milliampere, you want it to be 1 milliampere. But we know that anytime the VDS changes, right, we have some channel length modulation that happens. So if I come back to this source here and I said I have a constant VGS and I'm creating a current here, this is a current source that I'm going to use to bias other circuitry, this current would still move based on how this voltage is moving. So if I have a swing here at this point caused by some other circuitry, right, that swing will be actually causing a change in the current because there is an RDS, there is a channel length modulation that's going on, and that would cause a change in this current. So this is a current source which will not be, sinking a constant current all the time. As this drain moves around up and down, some swing, small signal swing or large signal swing, whatever it is, it will have an equivalent impact on the value of this current, because we know that in saturation the current is not flat, as we have seen the ID VDS curves, right? And since it is not flat, it's given by a finite, even though this value is large, it's given by a finite RDS and it will cause a change. So that's why we put this device in series with this, as we did here, because this guy now acts more like a shock absorber. There is a lot of swing that could happen here caused by other circuitry which are here. I have not shown that part, whatever else could be there. So if there is a big swing going on, it gets divided by the gain of this transistor, which actually absorbs all the shock, and finally this is very, very quiet. V1 node does not see a lot of swing. So for example, if there was 100 millivolt swing here, okay, at this point, drain, here 100 millivolt swing, all this 100 millivolt will fall across this and this current will change because of channel length modulation. If the gain of the stage is say 100, GM2 times RDS2 is 100, and you have 100 millivolt swing, what is the swing here? It has transformed that 100 millivolts into 1 millivolt because it's divided by the gain of the stage. That is the beauty of Cascode, is it boosts the output impedance, and it also acts as a shock absorber, so that the current which is really generated here because of its VGS and the VDS here, that VDS does not change much, and it helps with a very, very constant current. And that's how we make this technique is used significantly, cascoding, to generate very, very stable current sources. Okay, so in this example what we did is we solved for output impedance, and we found that it's boosted significantly by the gain of this intermediate stage that we put in, and it also helps as a shock absorber to attenuate whatever the voltage swing here is. It gets divided down here by the time we come to this a point here. So these are some of the examples of how you can take the simple small signal model and try to apply it to either find the value intuitively directly without drawing the model, which is what, as you go over time, you will not need to draw these models for most of the circuits. You will be able to find it intuitively quickly. But also, since it's the beginning now for you guys, just try to develop simple models like this and then work through it and see that you will be able to write some, without too much of complicated mathematics, you will be able to come to the answer, and also appreciate some of the beauty of just putting just a single device in series with it, how much benefit you get just by putting one guy in there. Okay, next we're going to start with the MOS, the capacitances. So all this time we developed the small signal model, and we said that we're going to apply some kind of a sine wave, but if the frequency is small, then only all the models that we talked about are valid, because we did not consider any parasitic capacitances. Like any other device, MOS also has parasitic capacitance, actually a lot of them, and they tend to make the MOS devices act like a low pass filter. What that means is they have a capacity, they can go up to a certain speed, they can go up to certain high frequencies, and after that they tend to lose their properties of like GM and all. They won't be able to create so much of a gain or current and all that stuff, mainly because all the parasitic capacitances tend to make the MOS act like a low pass filtering element. Okay, so it'll kill the gain and all that stuff. So we will see what are the different parasitic capacitances here in the MOS, and we'll go through them one by one and see there are the simple ones, which are the low hanging fruit, which is what we'll go through first, and then we'll go through the more complex ones, which are the more dominant ones. The complex ones are the more dominant ones, which is what we will see. And what it does at the end is, if you look at, or if you hear about all these different processes that you have, you will see, okay, olden days used to be, whatever the technology, 0.35 micron, 0.25 micron, 0.18 micron. Further, they will categorize like there is an FT. FT is a measure of the speed of the process. What that really meant was that you have a device and it has certain parasitic capacitances, and because of which there is only a maximum speed of operation you can do. But now as the device sizes have scaled down, these parasitic capacitances have scaled down. The parasitic capacitances are bigger when the device size is bigger. But now if you can make smaller and smaller devices, their parasitic capacitance is smaller and their speed has increased. So they have gone to tens of gigahertz or even hundreds of gigahertz now in many of them. So what causes this parasitic capacitance? Where it comes from? Let's try to review them. First, we're going to start with something which are called overlap capacitances, and they're always there. This is just a limitation of the fabrication process, the technology. You just can't avoid these things. What happens is, I'm trying to show the gate here. Okay, so this is the same NMOS. This is the silicon dioxide gate, and you can see the gate always has some overlap with the source channel and the drain. Why? Because during the fabrication part, when you're doping this with N plus material and you're doping the source with N plus material, after doping you go through a process called annealing or slow cooling. Okay, when that happens is, if you doped right till the edge, that doesn't mean the particles will actually be till the edge. They always slip, they will always spread out a little bit. And this is just natural. This is just something you cannot avoid. You can't just bombard it at a certain boundary and think that they are always going to be confined to the boundary. No, some of them will always spill out, and that is what happens because of spilling out on both directions, and they give rise to some capacitance. So from gate to source, there is always some overlap capacitance because of spilling up, and that is called CGS. So gate to source, O means overlap. CGSO is the overlap capacitance. CGDO is the overlap capacitance with the drain, and they're symmetrical. So these values are more, till now I've seen they're always equal. Okay, they are not asymmetrical. They are always they're the same. So this is the first set of capacitances that you get, which are called overlap capacitances. The next set that you get is, so we have this overlap. We looked at the overlap capacitances. Now is you have this N plus region and N plus region. And this is a P substrate. So this N to P, that forms a reverse bias diode, right? So we have two reverse bias diodes, because and hopefully you keep them reverse biased, because if any of them gets forward biased, then you don't have the MOS device anymore. This MOS will be shunted in parallel by this extremely low impedance diode, and it's not a MOS device anymore. So these P plus N, P to N plus diodes, right, they have a depletion region because they are reverse biased, and because they have a depletion region, they're going to give rise to some capacitance, which is again going to depend on the voltages. Okay, what is the source voltage? Source to bulk voltage. Based on that, you will have this reverse biased diode capacitance called C, source to bulk. Similarly, drain to bulk. In most of the time, it's the drain voltage that varies more in case of an NMOS. Okay, and same is also true in case of PMOS. So you don't really see a whole lot of variation in this thing, but you could see quite a bit of a variation in this diode capacitance when there is swing here. And if there is voltage swing, this is actually a nonlinear capacitor, right? So any voltage swing across a reverse bias diode could cause the capacitance to change significantly, and this becomes a big killer for circuitry where a nonlinear capacitor causes nonlinearity at the output. Okay, what kind of circuit, like power amplifiers, other amplifiers, where they have large voltage swing at the output? If this was an output node, like a drain being an output node, a large voltage swing here will cause a large voltage swing across this reverse bias diode, which will cause a change in this capacitance value, because we know that whenever diode is reverse biased, as the voltage changes, the depletion region width changes, and that has an effect on the change in the capacitance. So these are voltage dependent, could cause nonlinear capacitors. Nonlinear means it is changing over voltage swing. That is what I mean by nonlinear. But anyway, so these are the other two types of reverse bias diode capacitance: source to bulk, drain to bulk. Okay, so we have seen 4 of them, which are the low-hanging fruit. Now comes the 2 big ones, which are going to be what we have to go into much more detail, and they are actually the biggest capacitors. Right? They are the gate to source and gate to drain. Oh, somehow I flipped that terminology compared to, but you can still do it. That's fine, and I guess I corrected it here. Okay, so we have the gate to source and the gate to drain capacitances. What happens is, in order to understand this gate to source and gate to drain capacitances, which are the biggest one, first of all, you know that there is a huge, oxide, right? So we have a capacitor from gate to right this edge of the channel, or this edge, whether the channel exists or not, let's not worry about it. We'll call this as a capacitance C1. What is C1? C1 is Cox, which is actually the density of the capacitance multiplied by W times L. I think in the last lecture or the one before that, I might have confused you saying Cox is the oxide capacitance. It is not the oxide capacitance, it is the oxide capacitance density. It is the density of the oxide capacitance. To get the actual capacitance, you have to multiply it by the width and length of that piece of oxide. Okay, so that's why we multiply it with W and L. So that comes actually in series with C2. C2 is actually dependent on the channel. This is actually the capacitance of the channel. And then, so we have C1 and C2 in series, which gives you a capacitance like, the effective capacitance then becomes C1, C2 divided by C1 plus C2. So if we look at this more, when we are trying to calculate gate to source and gate to drain capacitance. Now I mentioned that there is a capacitance of the channel, which is C2. So let's try to understand how can a channel have a capacitance, right? Here is how it can have a capacitance. So normally, what is the definition of capacitance? Capacitance definition is, it is the rate of change of charge with respect to voltage. That is what is the fundamental definition of capacitance. So if you have some charge somewhere, and that charge was not changing at all with voltage, then you have no capacitance. It's zero capacitance. But if the charge, in any case, whether it's in a box or it's in a channel or it's in a something, if you apply a voltage and as the voltage changes, the charge changes, that means there is a capacitance corresponding to that. And that's why we have this famous equation called Q is equal to charge is equal to capacitance times voltage. Q is equal to CV. Okay, from there you can also just write this expression of C is dQ by dV. It is the rate of change of charge with respect to the voltage applied across it. So now what is happening in this thing? If we don't have any channel at all, of course there is no charge and there is no change in the change in charge with voltage is very, very small. So this capacitance does not really exist then, right? It's a zero. There is no capacitance there. But when the channel is formed, like in this case, specifically like in this case, I'm showing the channel is in the active region where the channel is all the way there from source to drain. Any change in voltage. So when we change VGS, okay, V gate to source, and here it assume that the bulk is tied to the source here again. That's the assumption in all these lectures. So whenever you change VGS, the amount of charge in this channel will change. So this dV becomes dVGS, right? And the charge in the channel is changing because of this. This is going to give rise to a capacitance. And that is this capacitance C2. So C1 is a fixed capacitance, which is Cox times W times L. And C2 is actually a variable capacitance, which is varying based on this gate bias, gate to source bias. Okay. It will also vary with the drain to source bias based on how it's biased, but we'll look into that later on. So C2 is actually the derivative of this channel, the charge in the channel with respect to V. V in this case being VGS. Okay, that's what we are considering. We are not considering VDS yet. We will go there in just a little bit, but not yet. Here we are assuming that VDS is constant at some value, and we are not changing it. So VGS is the only term that is causing this capacitance. So what will happen is we're going to have these two capacitances. Gate to source called CGS and gate to drain, which is called CGD. And we are doing it for, let's say, a constant VDS value. Okay, this exercise we will do it for a constant VDS value. So we don't have any capacitive effect coming because of VDS, because if VDS does not change, the charge will not change because of VDS. It will only change because of the gate being changing, and as the gate voltage changes, it will affect both these capacitors. So let's see how this goes. So we know that we have two capacitances, right? C1 and C2. C1 is always fixed. C2 is what we need to find out. So C1 is always fixed, C2. So when VGS is less than VT, that is, the channel is not there, then as we apply it, the amount of change in charge that happens in the channel being almost absent, the change in charge is very small, so C2 is almost small. So if this is the case, then what happens is we have got, this to this, this part actually what happens is, so when you have this is the smallest value. When you have two capacitors, the smallest value will dominate, right? So when two capacitors in series, it's kind of like opposite to the one with the resistors. In resistors, the biggest one dominates, and capacitor, the smallest one dominates. Okay, so here the smallest one in C2, so you will get almost no capacitance. So C1 and C2 in series becomes zero capacitance. So there is no capacitance here. And so what will you see from gate to source then? So you're not going to see any of this capacitance through the channel. So from gate to source, you will only see the overlap capacitance, CGSO. And gate to drain also, you will see the only overlap capacitance, CGDO. So this is what you see when the channel is off. Okay, you see only the overlaps when the channel is off. Now comes to the case, remember VDS is constant and we are increasing VGS. So VGS is increased such that now the NMOS starts to get on. Okay, it starts to get on, but still VGS minus VT, which is V on, it's less than VDS. What it means is VDS is still much higher than VGS minus VT. What is that condition for? That's a condition for saturation. So the channel will form, but the channel will form in a pinched off way because this guy is in saturation. So this is the picture for it's in the pinched off way. So when it's pinched off, what we say is we analytically model it. So first of all, what is C2? We have a channel, and how will this charge change now with respect to your voltage applied? So this C2, which used to be 0, now starts getting bigger. Okay, it is still smaller than C1, but it starts getting bigger. And as the voltage increases more, it will become comparable to C1. And then as the voltage becomes even a little bit more, this C2 actually becomes extremely large compared to C1. That happens gradually, and we'll see in a plot that it will happen gradually, but it starts from being a very small value to being comparable to C1 and then very large comparable to C1. So when this C2 becomes very large comparable to C1, C1 dominates because C1 is the smallest capacitance now. They're in series. And also when the channel is pinched off, what happens is, and again it's analytical modeling, it's simple first order analytical modeling. We say that we have all this oxide capacitance C1 here, which is Cox times W and L. How much of it do we see from gate to source? We just put an analytical number of 2/3. We say since the whole channel is not there, we will see 2/3 of this capacitance, of this parallel plate capacitor. We will see 2/3 of the C1 capacitance towards the CGS, and of course CGS always has this overlap capacitance. Okay, so CGSO is the overlap capacitance plus 2/3 of this parallel plate capacitance. That's what you're going to see as a part of CGS. What happens to CGD? Since the channel is pinched off, we only see the overlap capacitance. We do not have a path of C1, then C2, and then going here. We do have a path, but when we go through this pinched off region, it's high impedance. Okay, so it acts like a high impedance region, and that's why we do not see any of these capacitance effects, C1, C2 in series, that effect coming towards CGD. CGD is only purely the overlap capacitance because the channel is pinched off. So this is how we model in an analytical way. The simulators actually model it much more accurately with much more complicated expression, but this is a first order model which is still valid and pretty good, for hand calculations. If you wanted to find CGS, you could use this expression. Okay, so this is what happens when we have created the channel, but we have also remained in saturation. Next we go to the case where VGS is further increased. So now we're going to increase the VGS further. Then what happens is at some point VGS minus VT, which is V on, will become bigger than VDS. So whatever is our fixed VDS applied across this, now we have turned it on heavily where this is not in saturation anymore. It transitions from being in saturation into linear region. In linear region we have the whole channel. right? Again, there what will happen is you will have C1 and C2, but in the channel, a small change in this thing is causing a large change in this in the amount of charge. So C2 tends to still become pretty big in most cases compared to C1. We can make that assumption. So what you will see is you will see C1 with a completely on channel. Okay, so the channel is completely on from source to drain. So again, analytically, what we say is since the channel is on, now gate to source gets half of this parallel plate capacitor, this silicon dioxide box here. Half of it goes to this gate to source part and half of it goes to gate to drain part. That's why we get to these equations where CGS is the overlap capacitance, which is always there, plus half of this parallel plate capacitor, which is Cox times W times L. CGD, same overlap plus half of this. So CGS and CGD become equal at that point roughly. Okay, and again here we are assuming that C2 is pretty large because change in the gate to source bias is causing this channel to change, the charge to change very fast, such that this C2 is very, very high. So C2 does not dominate, it's C1 that dominates that at that point. Okay, so these are the three regions as we increase VGS, and that is actually, you will see this plot in some of the textbooks, is if you have the x-axis as VGS and the y-axis is capacitance, and you're increasing VGS, when VGS is 0, well, of course, you know, the MOS is in off state. Then at some point you turn on the MOS and the MOS device gets into saturation. But then as VGS becomes even higher and it becomes bigger than VDS, because our VDS is constant here, then it goes from saturation to active region. So what would these two important capacitors look like, CGS and CGD? When it's off, they both look as the overlap capacitances. And then as it turns on, as I said, there is a gradual change. It doesn't go boom from here to here. It has a gradual change over voltages where it will actually go from the overlap capacitances to the value which is overlap plus 2/3 of the parallel plate capacitor. Okay, that is where CGS will go. But since the channel is pinched off here, that's why we use the term 2/3. But the gate, since it's pinched off, it still remains at overlap capacitance. Then after that, as the VGS is increased more, where it's going from saturation to active region and the whole channel is forming, they both will gradually, one will come down, one will go up and converge to this value which is your overlap capacitance plus half of that parallel plate capacitance or the gate. Half of the gate capacitance is here. So they both will converge to here. So this is a plot that sometimes we use to show how is this capacitance changing, whether we are in saturation or whether we are in active, and sometimes this actually is used to make, similar concepts are used to make actually a voltage dependent capacitor. Okay, so this is one of them, and we'll talk about a similar thing in the next page, but hopefully now you understand this. So let me go back and review a few things. Okay, so first we talked about the overlap capacitance, which are actually negligible, which are small, not so big. They are not the dominant capacitors. We talked about the source to bulk and drain to bulk capacitors. They are also small, but where they tend to become problematic is when you have large voltage swing at the drain here, and if the drain point is the output, you will see a lot of voltage swing across this reverse bias diode. That will make this capacitance change with this voltage swing, which means this capacitance will become non-linear with voltage swing, and that will give rise to non-linearities of a circuit. Like an amplifier, it's not a linear amplifier, it will become a non-linear amplifier. You could see problems like that. Okay, again, these two are not the dominant sources that you have to worry about most of the time. These four you don't have to. What you really have to worry about, and what tends to become as we went through this section, is CGS always tends to be the biggest parasitic capacitor, and that causes the biggest frequency limitations that we see. How high of a frequency can you operate in? Okay, it is primarily determined by CGS. Okay, CGD also could become dominant based on how big these overlap capacitances are, but it is the CGS that you have to really worry about most of the time, and this is a plot that does that. So if you have seen in the literature, there is a measure, a MOS device, how fast it is. What is the speed of the MOS device? It is given by a term called FT, F and a T. FT for a MOS device is nothing but a ratio of GM divided by CGS. So if you took a single device, whether it's a PMOS or NMOS, and you did GM divided by CGS, that value is the measure of FT. FT is GM over CGS. That gives you the speed, because CGS is the dominant of most of all the other caps that you have, and you have to design to see. So wherever you're trying to design high frequency RF circuits, you are trying to design it to try to see what are the CGS. CGS is not so much in your control. It depends on what is the device size you're using, what are the W and Ls, right? You need certain W and Ls to carry some current, to get some GM, and that kind of puts a limitation on how much CGS you can get, and in a way it limits how fast can that circuit operate. Okay, what is the highest frequency it can tolerate. So this is the parasitic capacitances, and one of the things that we do is so these parasitic capacitances are always there in the circuitry. There is no way you can get rid of it. But what I have not touched here, but I can just kind of give you a little idea, is when we do these circuitries and we'll make these small signal models where we'll have capacitances, CGS will be the one that will kind of dominate it. And I think I have a model here somewhere. Oh, here it is. Okay, right. So let's just see how we change the model now. So here is the MOS device, which had no parasitic capacitance. It was our NMOS amplifier, simple NMOS amplifier with a resistive load. So how has it changed? Now we have put a few capacitors from gate to source. We have put CGS, which is the dominant one, biggest capacitor. We also have gate to bulk, another capacitance, and since our bulk is same as source, so I've showed that in parallel. Gate to bulk also I've shown in parallel with this. So this we didn't talk about, the gate to bulk, but there is always also a parasitic capacitance that will be there from this gate to bulk. Okay, so that's another parasitic cap which is from gate to bulk, which is also there. Now most of the time it's very small, but it's also there. So we have those two elements. Since this is the gate and this is the drain, we have gate to drain capacitance, as we talked about. From gate to drain we are going to have a capacitance, and that also will change based on how we are biased, whether we are off, we are in saturation, or we are in active. So that is the element there. If the voltage applied here is VGS, then we have the normal low frequency model still there. GM times VGS is the controlled current source, and RDS. And we always had it, we just put in all these capacitors now, all the parasitic capacitors. Then we have another one which is drain to bulk. So we have this drain and drain to bulk. We have this the reverse bias diode that we talked about, which could change based on the output voltage swing, and hopefully it is not big enough to cause an impact. Hopefully these other capacitances are big enough, or the output has a big capacitance, looking into the next stage or something. So that, since the bulk is connected to source, you can ground it here too. So that becomes another one. We also have this source to bulk capacitance. I am not showing in the model because they are connected, they are shorted out in this configuration. So I'm not showing just this piece of capacitor. Otherwise we are showing we have 5 capacitors here, 4 of them are here, and the 5th one I'm not showing because it's already connected, it's shorted out because bulk is connected to source in this assumption. If it's not, that model will be a little different. So and then finally at the drain you have this resistance R to AC ground. This is DC VDD, means it's AC ground. So that is how the small signal model changes from being previously what we had. And we will not go into deriving the gain again. We derived the gain previously, the low frequency gain. How does that gain change? Where are the poles and zeros, and what does the frequency response look like? We'll look at it some other time, but I just wanted to first show you that how this model gets modified because of all the parasitic capacitance that's coming in. One other point that I was going to make, and just to give you something to think about, is anytime you add capacitances and you have these capacitances are added on top of some resistors or some controlled current sources, if you solve this, this will give you a low pass filter type frequency response. What that means is you will have some gain of this amplifier at low frequency, and as the frequency gets higher, the gain will roll off. That is the low pass filter type response. So low pass filter is it remains flat. So let's say if it's a gain, it will remain flat like this, and then it will roll off over frequency, where this x-axis will be frequency. All of them have a low pass type filter response. And that roll off happens because of this parasitic capacitances, which we cannot avoid. Now when you have this parasitic capacitance and you can't avoid them in a technology, how could you do a more high frequency design, given that you have to live with these capacitances. What we do is, wherever we want to extend the speed. Okay, so let's say the circuitries don't have the speed and we want to extend the speed, and we have this parasitic capacitances, let's say a CGS, that we cannot avoid. What we can do is we can come and put an inductor in parallel with it, either in parallel or in series. Most of the time you basically put it in parallel. So whenever you have an L in parallel with a C, what happens is that LC circuitry will resonate. The inductor and the capacitor in parallel forms a LC resonant tank. And what it does is, and when it resonates, it becomes open circuit. It open circuits the capacitance. Okay, I'm assuming here that there is some concepts of LC that you know, but if you don't go, please go refer to the parallel LC resonant type tank circuits, and how a lossy capacitor could be resonated out by an inductor in parallel to it, and that way we extend the speed, because now that capacitor is not going to limit or give you a low pass type transfer function anymore. That capacitor has been knocked out by an inductor because it's resonating, and that's how we can sometimes use that technique in RF world all the time to resonate out losses, resonate out lossy capacitors with inductors, and extend the speed, extend the frequency of operation for the circuitry. So that is how we do it in RF, and that's where the inductors come in. A lot of these RF circuitries will use inductors, and primarily they are used mainly for resonating out some lossy capacitors. Okay, so just as something for you to think about. Let's see, since we talked about capacitors and all, let me try to end this sort of lecture here with the varactor. Varactor is a voltage controlled capacitor that we use. Remember that what we talked about here, if you have this thing and you had a constant VDS, this is acting as a voltage controlled capacitor also. The capacitor from gate to drain and gate to source, if VDS was constant, would look like this. So this is indeed a voltage controlled capacitor. It is changing with voltage, right? We don't use this configuration necessarily all the time, but what we use is a similar configuration, which will be like if you took this red plot and you went up and you just stopped here. Okay, we use that, and that is what is called a varactor, and how it is used is more like this. There are two kinds of varactors. I'll only explain one of them here. Okay, and this one is where the channel is normally off, and you're going to apply voltage to turn on the channel. One thing we do is we are first of all going to short the source and drain. So this is the drain, this is the source, which is shorted into a single terminal called B. This is not the bulk. I'm not even showing the bulk here. What happens to the bulk? You could ground it and all that, but this B is one terminal of the capacitor, and A is the other terminal of the capacitor, which is the gate. So the gate is one terminal of the capacitor, and the drain and source shorted is the other terminal. So this is where we are making the capacitor, okay, with the source and drain shorted as one terminal, and this is going to vary based on how the gate to source voltage varies. And we'll also make the assumption here that the bulk is shorted to source here, okay, for now, so we don't have to bring the bulk into the picture. The key thing here is, since the source and drain are shorted together, this NMOS remains in active region all the time. That is the key difference. Here we had a fixed VDS which kept it in saturation, and then it kept it in active. Okay, so we were in saturation and then we were in active. Now since VDS is 0, okay, since VDS is actually not 0 or a small value, okay, so our device will remain in active region all the time. That is, either the channel is off, or if the channel is formed, the whole channel is there. Okay, it's not going to be any different. So when VGS is less than VT, when the channel is off, what do we see? We don't have a channel. We only see the overlap capacitances, right? So that is the minimum value of the capacitance we'll have when VGS is low. So the y-axis is capacitance between A and B, and VGS is the voltage, which is same as VAB, voltage applied between terminal A with respect to B. Low voltages, you have CGS overlap and CGD overlap, okay, adding of both of them, because source and drain are shorted. That is also what we call as the C minimum. Then as the voltage increases, right, the channel starts to form. The channel starts to form even more. So when the channel is forming, remember we have these two capacitors, C1 and C2. When the channel is off, C2 is 0. But as the channel starts forming, C2 becomes bigger and bigger, and eventually it becomes so big that it gets dominated by C1, right? Because the smaller of the two capacitors will dominate. If C2 is too large, we only see C1, and the full channel is formed here. So that becomes the value of the C max, where we gradually transition from this lower value to the higher value. And what is the higher value? We will always have the overlap capacitances, and we add the total parallel plate capacitor now, which is Cox times W times L. So we go from a minimum value to a maximum value, and there is a range over which it is almost linear. Okay, so the capacitance changes linearly with VGS, and that is mostly the region where we will use these varactors. And that is what we call as the tuning range of these varactors that we use to make in the VCOs, voltage control oscillators, and maybe some other places you use. But if you use this varactor with it discretely, you could also do that where you say my VGS is 0, or my VGS is the highest voltage, say VDD. Then you would be seeing the minimum value and the maximum value. So you'll get two values of this capacitor, the min and the max. If you just operate at 1 point high only and 1 point low only, and you say I'm not going to have these operating points at all. But if you operate in this whole region here in between, you would actually see a very linear capacitor, capacitance changing with the voltage supply. Okay, so this is a varactor, which is an extension of what we just talked previously. The basic difference is source and drain are shorted together, so we don't have a VDS. The VDS is 0 all the time, or very, very small value of the voltage, and this acts as a voltage controlled capacitor. Okay, so that is the varactor here, and we'll continue on with the next section. So let's look at some of the current mirrors. I have the heading there as current sources / mirrors, but these are really more like current mirrors. These are not really current sources. So what happens is current sources are actually generated by certain circuits on the chip, which will generate a current. You have seen me use this symbol, like this is the symbol of a current source. Okay, I've been using an ideal source, but in reality inside, when you make a chip, you have some circuits made up of MOS devices. They're called band gap circuits, which are used to generate voltage references as well as current references. So something like this could be generated there. We will not be talking about those kind of circuitry here, but what I want to talk about quickly is the current mirrors, because when we get this current from somewhere, we use it through circuits called current mirrors to bias different circuitries. So I just wanted to kind of go briefly over some of the structures here. So what is a current mirror? Treat this black box as a current mirror, and what we are trying to do is we are trying to push a current into it, okay, some I in, and there will be a current I out going out of there, and this would be going to some circuitry. It could be an amplifier stage which needs a current, or it could be some other kind of stages. So some of the properties of this current mirror has to be, when you're trying to push current into it, its input impedance, which I call Z in here, or you can also say Rn if you don't want to worry about capacitances, because these are mostly DC current. There is no AC here. This is a fixed current generated in the chip, and we want it to remain fixed all the time. So there is really not an AC component there. So this could very well be written as Rn. That input impedance should really be very low, ideally 0, because the current would always try to go into a low impedance path. So the input impedance should be ideally as low as possible, and then this current mirror which mirrors this current, so I in is mirrored into I out, such that they are both equal, or some ratio, some number. Good, for now just keep it simple. Let's say they are 1 to 1. Then I out, you want I out to be exactly equal to I in, and also the impedance looking here at the output, you want it as high as possible, like infinity. Okay, if possible, because then all the current will go out and you will not have any losses in the circuitry. So the input impedance should be as low as possible, output impedance should be as high as possible. If you do that, your I in will be equal to I out for a 1:1 current mirror. Okay, so this is the basic property of current mirrors. How or what kind of circuitry looks like current mirrors? A simple one is this, which you might have seen. You have a current source which is actually generated from some other circuitry in the chip. It's giving you the current. You put it into a diode connected NMOS device, and let's say if this was 1 to 1, then it takes the current in and it mirrors the current out here. Okay, so I out becomes equal to I in, or if this is in some ratio, some 1 to n, then this will be n times of In. If you look at the impedance looking into it, we said that we want it to be as low as possible. The impedance is 1 over Gm. Anytime you see a diode connected device like this and you want to find the impedance of it, you can use the simple small signal model, okay, and then with that you would actually see that this is actually 1 over Gm. Okay, so this is what is a low impedance here that's coming in. Now the output impedance here, we said that once you mirrored it, you want all the current to go out. Remember, this MOS device, it's not ideal. It has got some losses too. What are the losses here? The loss here is RDS, right? That is the output impedance. Some of the current will actually get lost in RDS, and some of it, and most of it would go out. The higher the value of RDS is, the better is this current mirror, because then the input current is translated to the output side. Okay, so that is what we call as a current mirror. Okay, it's a simple NMOS current mirror, satisfying the laws of a low input impedance, output impedance is high. They're not very low or not extremely high. You could do things to make them better, but just for now, to get the concept, this is an NMOS mirror. Similarly, you can have a PMOS current mirror, where we have a PMOS attached, whose source is attached to VDD, and the drain and gate are shorted together. So anytime the drain and gate are shorted, whether it's a PMOS or an NMOS, its impedance becomes 1 over Gm. Again, for here also you can do the small signal model and convince yourself that it becomes 1 over Gm, which is typically a lower value of the impedance. Okay, so this is a low impedance node. The current will actually flow through here. It will get mirrored here. The output impedance, again in this case, is RDS. Depending on the value of the RDS, some of it will be lost, but hopefully not too much, and you have an I in to I out. The ratio is hopefully maintained, okay, even with all this little bit of losses going on. So this is a simple NMOS current mirror, which is used extensively everywhere. When you start designing circuits, you will just use simple circuit mirrors like this, either in NMOS or PMOS. Okay, and why do we do this is because, as I said, this is a current coming from some other circuitry on the chip. Okay, a biasing circuitry giving a current. You might have 5 different blocks that you want to provide bias current. Well, you cannot tell the biasing circuitry to give you 5 different currents. It can give you one, and then you build this current mirror. So here we are taking the input current and providing the bias current to some block. Okay, say block 1. If I put another stage here, I take this and I copy it over, and its gate is also driven here, then that could supply, that becomes a second branch to supply some bias current to another circuitry. So this way you can add many branches whose gate and source are common, and they will all provide the same current. Okay, so it becomes a way to take one current in and multiple current out to give to different blocks. So that's why we use this current mirrors, to mirror the current into various blocks. Okay, so we looked at the simple current mirrors. Now let's look at how we can improve, let's say, the output impedance. We did go over a cascode earlier, and we showed that when you cascode, when you have a single device and you put a series MOS device with it, the output impedance really gets boosted, and that is roughly, as we said, if it is the Gm of this device, the RDS of this device multiplied by the RDS of this device. So if we just said all the RDSs are equal, roughly, then it will become Gm times RDS square. So previously, here looking down, you had only RDS. Now you have boosted it by a product of Gm times RDS. And typically, in most of the applications using long channel devices, you could get Gm RDS. That's like the voltage gain of a single stage, which is Gm times RDS, that you could get it in the order of about 100. So going from here to here, you have boosted the output impedance significantly, and that is a good thing, because then it becomes an even better current mirror. You have actually degraded the input impedance a little bit, because first it used to be 1 over Gm, now it's 2 over Gm, because you have two devices in series. The impedance from this point to this point is 1 over Gm, and again from this point to this point is 1 over Gm. So if you add the two, it will become 2 by GM. So the input impedance has degraded a little bit, but you have boosted the output impedance significantly. So this is one way by cascoding, and I think I mentioned this earlier, is cascoding is very popular where you have to boost the output impedance of a current source. So this acts as a current source, and this is a current mirror which is taking an input current and then mirroring into the output, and that becomes like a current source, and you have boosted the output impedance of this current source. Now so this is good, but see, one of the problems I wanted to highlight is this is difficult to do in today's technologies is because what we call is a headroom issue. You have to have voltage available to be able to do this. What do I mean by that? What is the DC voltage that's going to be here? That DC voltage is going to be Vt plus V on. V on being VGS minus Vt. Okay, whatever the VGS minus Vt value. So we have a VGS here, which is Vt plus V on, which is the voltage here. Now from here you go up again another Vt plus V on, right, which is for this device. So you have one VGS here and you have two VGS. So it becomes 2 times Vt plus V on becomes the voltage, and this could be a pretty high value of the DC voltage, could be even comparable to VDD or maybe even more than VDD in some of the submicron technologies. So for the structure to work, this voltage should be much lower than VDD, so we have some headroom left here for the current source. Okay, this is an external circuitry providing a bias current. We have to have, so we can't have this node at VDD and this node also at VDD such that we have zero voltage drop between the current source. No, in reality you cannot make a current source like that. You need to have some drop, some 200 millivolts or more drops across this. So that way when you put Vt, let's say Vt in submicron technology is almost like 500 millivolts. So 2 times Vt is 1 volt. V on is about 200 millivolts. Let's say you design it for, so that becomes 400 millivolts. So this is 1 volt, 400 millivolts. This, when you add up, becomes 1.4 volts. 1.4 volts is actually a pretty big number, given that these VDDs are almost 1 volt or 1.2 volt now in the submicron technologies. So this kind of structure is good to use if you can when you have the voltage headroom. When VDDs are higher value, you're using older processes, you can use it. But in the current day processes, this becomes difficult to use. So I wanted to emphasize that. One way you can go from this structure to this structure here, it's similar. The output part is similar. You still get the boosted output impedance of roughly GM times RDS square. So that's very good. In input part, what you have done is you have taken this gate and you are not shorting it here. You have taken it up all the way and shorting it here, and the gate of this is shorted there, and in between the two gates you have put in a resistor. Okay, so when you do that, it looks a little complicated or funny, but let me explain a few things here. This point here is going to become, your what is the voltage here? The voltage here is going to be Vt plus V on. At this point it will become Vt plus something. Let me say why do I have a 2V on here? The voltage drop across this R, if you work it out, you will see that whatever is the voltage drop across this R is pretty much the VDS that will be across this transistor. This transistor is going to take a current. We do not want this transistor to go into into linear region. We want it to be in saturation. Since we want this to be in saturation, what we have to do is we have to maintain a certain amount of voltage across it, and that voltage what we call as VGS minus Vt or V on. So that's why I'm saying that let's maintain it at least VDS of V on, so this guy remains in saturation, it doesn't go to active. Okay, so if this is V on, this voltage here across this resistor also becomes the same, V on, and again you can work it out. So this VDS is same as this one here, V on. So the value of R you will pick is V on divided by I in. Whatever is your bias current coming in, that divided by V on. V on, let's say, is 200 millivolts. 200 millivolts divided by whatever your bias current is will give you the value of the resistor. If you did that, then the voltage drop across this is a V on. At this point you are anyway sitting at Vt plus V on was the voltage here. So what will be the voltage here? It will be Vt plus 2 V on. So what you have done is, now look at this gate here, this gate, and compare it with the gate here, okay, in terms of the absolute DC voltages. You have a 2 V on number, You also have a 2V1 number. But here it sits at, you have a 2VT here, but here you only have a VT. So that is a way where you can make it work now with lower voltages. For example, if this was 500 millivolts and this value total is 400 millivolts, 2 times 200 millivolts, that's 900 millivolts. So if you have 900 millivolts here, let's say VDD was 1.2 volts, yes, you can make this circuitry work in the low voltage technologies. But for high voltage technologies, we won't be able to. We don't have a problem because there you can just use this. You don't have to do all this. So this is one of the other modifications you will see, and in industry it's quite commonly used, this kind of structure to make a cascoded current source. And this is how we make these current mirrors. And I guess, let's see, some of the notes that I have here are for like whenever you make this kind of a cascoded structure, you might be asked that, okay, if you have a choice, let's say in a technology I gave you long channel devices and also short channel devices. Okay, where would you use long channel, where would you use short channel devices? So let's see, why would people use long channel devices? Long channel devices have actually very low value of lambda, which means they have got high value of RDS. So that is good. You want high value of RDS. Then why don't we use just long channel devices all the time? The reason is, when you use long channel devices, first of all, you are trying to get a particular W over L. So if L is higher, your W is also higher, right? So let's say you had L of something and you said, I'm going to double the L to get better RDS. Well, you have to also double the W then to maintain the same W over L. Now, how big has your area increased? Your W has increased twice, your L has increased twice, and you have made the area 4 times. Okay, so first there is an area penalty. That is why, one of the reasons why we cannot just use long L's. The second thing is, which probably doesn't matter so much here, but you could also have when you have increased your area 4 times, the capacitance, the parasitic capacitance also gone up 4 times. Let's say if you were limited by some parasitic capacitance, that has also gone up 4 times. So that could have an effect based on what is attached here in the circuitry. You don't want to increase the parasitic capacitance at this point. Okay, so here it might be okay because this is only carrying DC currents, but here it may not be okay. So that's why what we do is, typically, if you have the choice and if you have the liberty, you would try to use these bottom devices with long channel devices because they have good RDS and they would do very good mirroring. Now, what are these devices doing? This devices is providing gain, GM times RDS, right? By the gain of this device, it's boosting the RDS of the bottom device. Here, if you have the liberty to use long channel, definitely use it. Long channel is always good. There's nothing wrong with it. But if you cannot tolerate the area, or if you cannot tolerate the capacitance, then you can use short channel lengths here. Because all you're trying to do here is get this term, GM times RDS, okay? The gain. GM times RDS. How can I maximize that value of GM times RDS? Well, obviously having a long channel length helps you maximize that because the RDSs are better. But for short channel, even though the RDS degrades, you might be okay. You might get enough gain from this stage and still keep its area smaller and the capacitance smaller. So that is one note I wanted to share to make sure that you can use it when you do the design. So the bottom ones, always try to use long channel devices for getting very good RDS, because if the RDSs match, the VDSs match, they are going to do very good mirroring. And here you can use both long as well as short channel based on what your constraints are. So this is some of the circuits which we call as current mirrors, and from these current mirrors we use them everywhere. And one of the places that we will use, which is what we're going to talk next, is in this amplifier. Okay, so we have looked at this amplifier before, but I have now tried to redraw it with a little different way. So let's start from here. Since we talked about current mirrors, let's see how the biasing happens, and then we'll go into this amplifier stage. Okay, so here is a bias current that is coming from some other part of the circuitry. Okay, it's giving you one current. You put it into a simple NMOS current mirror as we talked about, and you provide a bias current here. Okay, I think in the previous lectures we have talked about it, where I have showed it as a current source. Now I'm not showing it as a current source, even though this M3 is actually a current source. I'm showing it with an actual device that is implemented as a current source / mirror. Okay, so this is where we need it. We need to provide a biasing current to this amplifier. That's why we need a current mirror here. Okay, the rest of the circuitry we have seen previously, so we are just going to go through it. Previously we have only gone through finding the gain at DC and low frequencies. We have not talked about how capacitances affect the gain, which is what we will talk about now, and and then go from there. So this is a differential amplifier comprising of M1 and M2 with a bias current here. And the applied input is shown V in here. This is the input which is applied between these 2 points. Then we have RL as a load resistor, and some CL is the output capacitance. So this is a load resistor and a load capacitor. And then we have differential output voltage. So we apply an input here, and this is our output, and this is going to act as a voltage amplifier. We want to calculate what is its voltage gain. We want to calculate, what is its frequency response, what kind of Bode plot response it looks like, how does the gain roll off over frequency, and all this stuff, and that's what we will do. Okay. So what is the first thing that we do? So one thing that I want to stress here is this example, as well as many other examples. What I used to do was, and you should also do it, even though I'm not doing it here, you should also do it. I used to take this thing and just make a complete big small signal model. I'll put a small signal model for M1, I'll put a small signal model for M2, connect them all together with all the RL, CL, and everything that is there. So I'll start with a giant big small signal model, and I will derive a lot of equations, and then finally I'll come to the answer. That is definitely a good exercise to do, which you should also do it. But at the end, what happens is, when you have done all this mathematics and all these derivations, you also have to interpret the results intuitively. What are these equations telling me? Sometimes these equations get so big that we get lost in it, we get drowned in it, and we cannot really interpret the results. So what I'm doing here is I'm skipping the derivation part of it. You should not skip it, you should practice it, because that is also important as a part of the understanding. I've done it myself, that's why I'm just trying to skip it. But what I will show here is how can you intuitively derive what you're trying to derive without drawing a complete giant small signal model. How can you do it? And that's what I'm going to do here. So again, in no way I mean that you should not do derivations. You should do the derivations, but also keep in mind that intuitively, how can I come to the same results, same approximate results, or how can I interpret the results of the derivations are also important. So let's see the first level of circuit simplification. How do we go from here to here? We don't need to worry about all this, because all this M3 works is its gate voltage is never going to change. It's a fixed DC current. So it's a DC voltage. Its VGS will never change. So what does M3 look like? M3 just looks like an RDS in small signal model. Nothing else. Secondly, we are applying a differential input. Anytime we have a differential stage like this, which has a Vin applied here like this, differential input, you can break it into two inputs. You can say one side has Vin by 2, the other side actually has minus Vin by 2. And if I put the two in series, you can see this is ground, and if I connected the two in series, these two will add up and give you Vin. So you can break the differential excitation into two differential excitations like this, and apply them with respect to a common ground, and that is a major simplification that we can do when we are doing differential analysis. Here it's a differential signal. You also have common mode analysis, which we'll talk about later, not here, but the simple thing to know is you have a differential excitation, you can break it into two sources like that. So when you apply here a positive signal and a negative signal, what happens is this point, which is common or in between to both of them, it automatically becomes AC ground. That is why we broke this. We broke this into two signals which are equal but opposite in magnitude. Okay, so this is Vin by 2, this is minus Vin by 2. When you do that, this point automatically becomes an AC ground, and what that does is it even helps us to get rid of this RDS3. RDS3 does not come into the picture anymore, because this is also ground. Then what is the VGS applied to M1? It's Vin by 2. What is the VGS applied to M2? It is minus Vin by 2. Okay, so VGS becomes equal to this voltage because this is AC ground. Now looking at that, now what the circuitry has become is, if I slice it through the middle, the left half is same as the right half. They are symmetrical now, right? They are symmetrical here too, but I just wanted to simplify and show you that now you can slice it and make it completely symmetrical. And that half circuit, I can draw a model now, small signal model. So here is so I'm just going to draw the half circuitry on the left side. Okay, so what does this look like? So I have the gate and the source. The source is grounded. Source and its bulk. I'm not showing the bulk, but again we'll make the assumption that the bulk is grounded here. Okay, so this is the gate to source where the V in by 2 is applied. Right, this V in by 2 falls right across gate to source. What all do we have going from gate to drain? We are going to have CGD. We are also going to have CGS and C gate to bulk. Those capacitances will be there. And then from drain, this is the drain point. From drain, we have got the dependent current source GM times VGS. Okay, we have got the RDS, which is also to ground. Then we have got the drain to bulk. So there is a parasitic capacitance that will be there from drain to bulk. So we're going to see the drain. Then we have this RL attached to AC ground because it's attached to VDD, and VDD is since it's a fixed DC bias, it's an AC ground. And then what is the capacitor? This is the output capacitor. Each node has CL, so I'm just putting a CL here. And what does this output become now? Output becomes V output by 2. Why? Because V output is the differential output. V in was the differential input. The way we broke the input, similarly you can break the output into two parts, and it will show you as V output by 2 as what becomes the output. So this now has become a simple model for us to actually solve. And how are we going to solve it? So here are a few things first we'll solve. We have a lot of capacitances here, but you can just neglect it and you can say, what is the DC gain? That's the first thing that we always find out. What is the gain at DC and at low frequencies, where these capacitance effects are not going to come into the picture? Okay, so the DC gain will be defined as, V out by V in, or V out by 2 divided by V in by 2. 2 and 2 are common, so they cancel out. So effectively, this is the DC gain at frequency of 0. If the frequency is 0, what happens to all these capacitances? They are open circuit. They have got an extremely high impedance, and all that remains is this GM remains, this term remains, RDS1 remains, and RL remains. So the effective parallel resistance of the output is RDS1 parallel to RL. That is the effective output resistance. And then since it's GM times VGS, that becomes the current that's going to go there, and it actually is going to go opposite way, right? Rather than going out, it's going in. That means we have to put this negative sign to force the current to go out. So the current that's going to go out is minus GM times VGS. So that current multiplied by the effective parallel resistance gives you the output voltage. VGS is same as V in by 2, so you can cancel all that, take that out, and effectively you will get this as the expression, minus GM times the effective output resistance, which is a parallel combination of RL and RDS1. Okay, so this gives you the DC gain. So we have found the DC gain. Then the next thing that we are going to find is find that we have got the DC gain because we assume that all my capacitances are absent. Okay, and they are really going to be open circuitry at that frequency. So remember what I'm trying to do is, if I took this circuitry here, right, I can actually derive the whole thing by changing the impedance of a capacitance. Let's say CGD. The impedance of a capacitance is going to be 1 over S CGD, right? If you're trying to find an S domain transfer function or in omega, whichever you're trying to do, I can derive it by applying Kirchhoff's current law and Kirchhoff's voltage law everywhere and derive that big equation. From there also, I will be able to find the DC gain, and I will be able to find the poles and zeros, which is what we'll find next. But here what I'm doing is, I really want you to do the derivation and then compare and see that these intuitive results actually make sense. I'm trying to derive these things intuitively without getting into the complete equations. Why is it important? Because even deriving this simple small circuit like this needs a lot of derivations. And when the circuit becomes big, like op amps and all, it's going to get even more complicated, and that's where this intuitive way of deriving will become more and more important for you. So intuitively, it's straightforward. We found the gain. Now what we want to do is we want to find the poles. okay, and the poles and zeros, which are there in the circuitry. So this is what is shown as a border plot, where we're going to show various poles and zeros and everything. So we'll plot that. But I hope that you know what a border plot is. A border plot is where we show that we have the y-axis is a gain. In this case, it's a voltage gain we are trying to do, okay, because it's a voltage amplifier, but it is the output that we're trying to measure, the y-axis, and the x-axis is frequency. So whatever the quantity we're trying to measure, in this case the voltage gain, how does the voltage gain vary over frequency? Okay, and poles are defined as frequencies where it tends to pull the response down. Those are called poles. They will cause a roll-off, downward roll-off. And what are zeros? Zeros are the case where it will actually pull the frequency response up. So poles give it a negative slope, pulling down. Zeros will tend to pull it up, and that is what we're going to analyze here, and we're going to come up with the shape of what is the frequency response look like. How will its gain be if I'm at a low frequency, or if I'm at a intermediate frequency, high frequency, whatever it is. Okay, so that is what we are going to go through here and determine the various poles and zeros. Because once you determine the poles and zeros, then in a way you can actually just plot the approximate transfer function, which is all you need, and that would match pretty closely with the derivation. If you did the derivation, and the derivation also is a function of frequency, then you put that and you plotted that frequency response, that should also look like this, similar to what you're deriving intuitively here. Okay, so we're going to go and look into these poles and zeros, so that's what let's look at next. So here again, I briefly described what is a Bode plot, but it's a plot over frequency of a quantity, and mostly this y-axis we try to put it in dB scale. We don't put it in absolute numbers, we try to put it in dB scale, and we look at both gain and phase. Here I'm not going to talk about phase yet, we are only just going to talk about the gain, the voltage gain, and how it will be affected over frequency. So we'll look at that. So we found the gain, the DC gain. Now let's look at the poles and zeros as we talked about, and again I will try to find them qualitatively, intuitively, to find out how many poles are there and how we can plot them in this Bode plot. So I tried to put everything in a single piece of paper and made it a little more congested here, but I'll try to still explain. So first of all, let's see. So what are poles? Poles are like, first before you find the poles or the zeros, what you have to see is what is the signal flow. If you're trying to do it intuitively, you have to look at what is the signal flow and through how many nodes is the signal flowing from the input to the output. So for example, this is my input here. Since this is grounded, we will not consider that. This is one where we apply the input. So what is the next node? As the signal is flowing from input to output, the next node is actually output itself. So we don't have any intermediate nodes from input to output here. So this is great. We have an input node, we have an output node. Now let's look at the input node. Okay, before looking at the input node, the reason I'm trying to find the nodes, how the signal is flowing, is because at each and every node, the signal will suffer loss. The signal will suffer loss if you see a pole. So each and every node it goes through, it's going to have an associated pole with it, and that is what we will find. So if there were 3 nodes, we'll have 3 poles, which we should be able to find at each of those nodes. Here we have only 2 nodes, so we should have only like 2 poles. Let's start with the input here first. In this particular configuration, the input is driven by an ideal voltage source. I did not say here that this is an amplifier, and when I say V in, I'm actually assuming that it has got 0 ohm source resistance. Normally a voltage source will have some series source resistance, but here the assumption is there is no series source resistance because I haven't really described it, and in many of these derivations we don't consider that. So if it's 0 ohms, this is an ideal source driving a node like the input node. Here we have capacitors, which are lossy capacitors, but since it is driven by an ideal voltage source, it's not going to cause any loss. You have whatever V in by 2 you apply here, at this node it's always going to be V in by 2. irrespective of whether you have a large capacitor or a small capacitor, it doesn't matter. So this is not a point where we are going to get a pole. If this source had a source resistance, some R, that R along with the C would form a pole. Because as the frequency increases, this capacitor will get shorted and eventually it will go to 0 ohm resistance. So if you had a source resistance here driving a 0 ohm, right, you will not get any of this V in at the output. So that would cause a pole because it will be loss in the signal. But since we don't have any source resistance, there is no losses at this point, so no pole here. We don't need to worry about it. So first one is gone. Let's see the second node, which is the output itself. Going from input to output, we just have gone through one shot itself. So what is the pole here? So the way you find the pole is actually like is going to be dependent on what is the total resistance at that node and what is the total capacitance at that node. These are the two things you need to calculate. It's an RC pole. Okay, so we need to find the total resistance seen at this point, which is what I'm calling as total R out, and the total capacitance seen at this point to ground, which is total cap. Okay, so let's see how we come to these expressions here. So if I find the total resistance, what is the total resistance? The total resistance is RDS1 and RL. These two are in parallel. That is the total resistance we find. Now what is the total capacitance at this point? We have CL, we have C drain to bulk, we go back, we also have CGD. Why? Because when you're looking at this node, you're assuming that there is no input. This input is shorted. So if it is shorted to ground, this is AC ground. So at this point, CGD is hanging to AC ground at this point, means all of the CGD. This is almost like CGD is kind of, the gate portion is grounded when you're trying to find the pole here, to find the total capacitance. So we have got three of those guys added here. You can see CGS or C gate to bulk for this device does not come into the picture because they're driven by an ideal voltage source with 0 ohm source resistance. That's why they don't come into the picture. Otherwise, they would also come into the picture. So those three capacitances make up the total cap at this node. We have the total resistance. So you can model it like saying, okay, total resistance and total capacitance, it becomes an RC pole. What is the formula for the pole? It's -1 over R and C. R being the total R and C being the total C. That is what will give you a pole. So if you look at the plot, it starts with a gain here, which we already found out is GM times the effective R. The effective R is RDS1 parallel to RL. That is the low frequency gain. It keeps going, and this will actually dip down 3 dB at the pole location. What is that approximate pole location that we found out? Is given by this expression. At that point, this will start to roll down and it will be a 3 dB loss. After that, this will keep going down as 20 dBs per decade. So if the frequency increased a decade, this roll off will be 20 dB because it's a single pole roll off. That is, those are the fundamentals from Bode plot. If you plot the gain in dB, then for every decade, a decade means 10 times. So if it is P1, you have some value, 10 times P1, it will actually be down by 20 dB. So that's the slope, 20 dBs per decade or 6 dBs per octave. 6 dB per octave. Octave means every doubling of frequency, the frequency doubled. So because of this pole, the gain will start going down. Okay, and why is the gain going down? What is really happening? What is happening is this capacitance are getting short over frequency. As their impedance is becoming smaller, they are actually shunting these resistances. So the current is still there, GM times VGS is still there, but that current has to be multiplied by the total impedance here. At low frequency, it used to be depending on the resistors, which were bigger. At higher frequencies, this capacitant impedances are becoming smaller, and that's why your gain is becoming smaller, your output is becoming smaller. It's I times the effective impedance value. And all these capacitance becoming lower and lower impedance just causes the gain to go down linearly. Then what happens is, something interesting happens, which is this circuit also has a 0. I told about we calculate the poles by looking at how many nodes are there, so that's true. Okay, we'll have another example where we'll go through this kind of a qualitative analysis again to find what are the different poles there. But this circuit also has a 0 like many other circuits. And what causes a 0? Okay, so the way the 0 comes is One of the ways the 0 comes is, as the definition says, the output has a 0, means at that point the output is 0. How can the output be 0? One of the way it comes is when you find two paths from input to output. If the signal could flow through two paths, okay, then the summation of the two paths could cause a 0 at the output. So here what happens is, if you look at the signal, right, the signal flows from input to output through a CGD, so that's one path. It also flows through GM times VGS, that causes the current here. That's also the another way it goes to the output. So every time you have more than one path, it is bound to give you a 0, because there is some frequency, some condition at which the output will be 0, and that is what we are going to use here in the approximation. So here is the input. Gate is where the input is applied. You can see from gate to output, it goes through there is a capacitive path where it can go. The other path is whatever the VGS is, GM times VGS also causes a current. So when the output becomes a 0, what happens to this point? This becomes like an AC ground. So what you will simply do is, if this is AC ground, which is where the 0 is happening, and that's why we call it a 0, you want to, what is the current going through here? The current going through here is V in divided by the impedance of this is going to give you the current, right? That current becomes equal to GM times VGS. VGS in this case is V in. So if you write the equation that the current going this way is actually coming this way and none of it goes out, such that the output is 0, okay, you can easily find it as V in divided by, the impedance is V in times S times CGD. That gives you the current here, and you turn all that current around and say all of it goes to GM times VGS, this controlled current source, and nothing goes here. So when you put the equation, you will see the 0 is caused at GM1 or GM here. Okay, I have this as GM, but it's basically the GM1 is the GM. Okay, that divided by CGD. So it's GM over CGD is typically where we will cause a 0 with a minus sign. And as we will see later, the 0 could be on the left half plane or the right half plane, and they cause problems, especially when they're in the right half plane. I think this is not a minus sign here. I think this is a plus sign that we should have, and I think I made a mistake here. It's a right half plane 0, and that will actually cause problems. Right half plane 0 is always cause different kind of problems. We'll see that again. Okay, so we calculated a pole, and hopefully now you understand that when you have multiple paths, it will also form zeros, and you can simply, in a very qualitative way, calculate it without solving the whole expression. If you did the whole derivation, you will get the same 0 there too. So we had a pole, now it goes down. At some point we hit this 0, and since it was going down this way with a single pole roll off, then it becomes more flat because of a 0, because the 0 tends to add a positive slope to the existing slope. So the existing slope was negative minus 20 dBs per decade. Now 0 will add plus 20 dBs per decade, so it becomes a flat. Okay, so this is a little weird kind of a transfer function. You can see it starts with a gain, it loses it, then it becomes flat this way. And sometimes people will ask, why does it become flat? Can you intuitively explain? You might have done a lot of derivations and everything, but can you intuitively explain what's going on here? So let's go back to the circuitry here and look at it. What happens at extremely high frequencies, right? The 0 and beyond this, it becomes flat at high frequency. At high frequency, you can actually throw out a lot of this stuff and show that this becomes a simple capacitive divider circuit. What I mean is, there is an input. The input goes through this CGD, and at the output, you can just show that all these caps at high frequencies, their impedance dominates, so you can get rid of RDS, you can get rid of RL, you can also get rid of this thing if you want, but effectively what it will become is, it will become a CGD in series with some effective capacitance to ground at the output, and that becomes a capacitive divider, which is almost like a resistive divider. But if you work it out, you will see it has similar kind of expression, but what it will show is whatever the input is, the output is going to be a fraction of the input based on the capacitor divider value. So because it's forming a capacitor divider, and I'll let you work it out more and see, it kind of tends to give you sometimes a flat frequency response, which also explains this nature of the curve that we have here. Okay, so so this was one example where what we did is we took a circuitry, we did some simplification, we made a simple small signal model, we found out what is the DC gain, we found out how many poles are there and what are their approximate expressions, pole and zero in this case, and we did a Bode plot to show how will this gain change over frequency. Next, let's take another amplifier example which actually is more relevant, because this will lead up to what are called as two-stage op-amps, and we'll go through two-stage op-amps separately, but this is one of the gain stages of the two stages op-amps. So I thought maybe this is a good example to go through intuitively to understand that how we calculate gain, what are the different poles and zeros and all the stuff that we have here. So what we have is, let's start with the biasing part. There's some bias current generated and it's fed to us, so we accept it, and this is an NMOS current mirror, same as before. We feed it. This bias current is used to bias this differential stage M1 and M2, same as before, where we have the differential input as Vin. The load right now is just the different. Rather than having resistive loads, we have actually a PMOS current mirror load, and this is very widely used, and it has a single output. So it has a differential input, it has a single output, and let's see how this thing provides gain and where are the different poles and zeros in the circuitry. Okay, so this is also an amplifier, and again the output has some load capacitance modeling the load that it could be driving. Okay, so the first simplification is same as what we did before. We have a differential source, so we'll break it into two sources, one side being Vin by 2, the other being minus Vin by 2. So differential, if you put them, it becomes Vin, and since this is acting as a current source, there is no change in VGS, it's constant because this is a constant DC bias, so this becomes an RDS3, but we can also neglect this RDS3 because this is AC ground. We have two opposite equal magnitude but opposite polarity signals, so the middle point automatically becomes a ground to a differential signal. So this can be further simplified here, and what I'm trying to show is I'm going to take a part of this circuitry and try to show how the current is generated in one part of the circuitry and how the small signal current is flowing. So first of all, we are going to eliminate RDS3 because this is AC ground. Next, I will only consider M1 and M5, only these two transistors, and go here. Okay, so what is M1? M1 has a very small signal at the gate called Vin by 2, and this is AC ground, which is this point. So what is the current that is created here from the small signal? It is GM1 times Vin by 2, right? That's the small signal current. Of course, in parallel, we also have RDS1. Now, at the output, what do we have looking up? Looking up, we have this diode connected PMOS device. What is the impedance of the PMOS device when we look into a diode connected structure? It is roughly 1 over GM. That's why I've just simply changed that as a 1 over GM5 of this device. I'm not putting an RDS here because if GM times RDS is big, that is what we are assuming, that GM times RDS, let's say, is in the order of 100. Then this is 100 times smaller resistance compared to an RDS of this device. That's why I have not drawn the RDS here. So the current that it created here, and again I'm not putting any capacitors or anything because I want to first find what is the DC gain, and then we will put capacitors to find the poles. So here the current, the GM times Vin by 2, the current that is created, is seeing two paths that it could split into. There is a low impedance path, which is 1 over GM, and there is a high impedance path, which is RDS1. Where do you think the current will mostly flow? Most of the current is going to flow through this PMOS device. It's going to go into this PMOS device, the diode connected PMOS, and flow through it. So 99%, so if GM RDS value is 100, okay, 99% of this current will flow here and only 1% will be lost here. Okay, So for now, let's just assume we are not worried about the 1% loss. All this current here flows through here. Okay, GM1 V in by 2. That is the one that I'm trying to show is whatever the current was created in this MOS device, all of it is flowing through this PMOS. I could have made the small signal model for this. I could have made the small signal model for put it together. It just becomes sometimes difficult when you try solving the equations. So intuitively, this is how I'm solving it to show you what current will go there. Okay. Now we simplify it and go further. So we know the current here is this value, right? Now we come to this and we said, okay, we have already looked at the left half of this circuit. Now let's see what happens to the right half of the circuit. So we said that this M5, which is here, was approximately carrying this current, right? Which was generated in M1. If this carries a current, and this is a current mirror, and this point is AC ground, so whatever current it carries, we are just going to simply mirror the current here. This is also going to carry GM1 V in by 2. Why? Because that's what a current mirror does. Even though there will be like 99% of this current will come here and 1% will get lost, but we are not worried about that 1% loss. We will just say this is a good current mirror. Whatever current is here is here. Okay, so the current flows here. Now let's see what is happening to this M2 here. So M2, whose source is AC ground, has an excitation of minus V in by 2. So if you have minus voltage, right, normally whatever the VGS is, GM times VGS current goes down. But since VGS is negative, the current will actually go up, which will be GM2 V in by 2. That is the amount of current that this guy will carry, and this current hits again, you know, the paths where there is an RDS2 here, right? So it's also going to have its own RDS here, and it's going to see the RDS6 of that one also. But eventually what will happen is this current that's going out will actually go all the way out. So we have got two currents. Okay, the current from this device, right, and the current from the top. They both, if you look at the direction, they're equal in magnitude, but they are both coming into this node. So if both the currents are coming into this node, they have to go out, right? And when they go out, what do they charge? They charge up. So since we are looking at DC only, they go into some resistor load and go from current to voltage. What is that voltage is going to be? So the total current coming at this point is this term plus this term. What is the total resistance? So okay, let me go down here to see. So the total current coming here is the current from the top and the current from the bottom, both coming here. They are written here. What is the total resistance? RDS6 and RDS2 in parallel. So we have the total current, the total resistance, and that gives you the output voltage, right? So that's going to be the output voltage. So from here, if you find the gain V out by V in at 0 or DC or low frequencies, it becomes, since GM1 and GM2, so this is symmetrical on both sides. They're going to carry, they have the same sizes, they carry half and half of the current and all that. So you can just say GM1 or GM2, they're both equal. So that value multiplied by the total RDS at this point. So this is a structure which has given you huge voltage gain from input all the way to the output. If GM-RDS is in the order of say 100, then since there are two of them in parallel, this value will be 50. Right? Because this if both the RDSs were equal in a way, roughly you will have RDS by 2, so roughly this will be a gain of 50. So these amplifiers, which is actually used in one of the classical two-stage op-amp topology, this is the first gain stage of it, could provide huge gain. So that is the DC gain that we have determined without actually making the small signal model of 4 transistors, because believe me, if you had 4 of them, it will get pretty complicated to kind of still manage it. But this way, intuitively, just tracing the currents, what voltage causes what current, where do the current goes, and then finally what current goes out to the output, and what is the total resistance there, that gives you the V out. So that's one way you can find the gain. And as you work through different kinds of circuits, you would get really good at doing these things of tracing You have a voltage, how much current is there, what path the current is going to go, what are the different paths, and which is the lowest impedance path, and it will so all that stuff. So we got the DC gain. Now let's see where are the poles and zeros. Okay, because what we eventually want to do is we want to plot this frequency response, and we'll come to it. So poles and zeros. Let's see how many nodes are there from input to output. These are the inputs, right? Here is the output. So what are the ways you can go from the input to the output? Let's see how many nodes we have. First, this is the input. We can go straight to the output this way. So output is definitely one node where we're going to have a pole, and that is what we'll calculate first. But if you go from this side of the input, you hop to this node, right? And then you hop to this node. So this is one node where we're going to have a pole. This is also a node we are going to have a pole, because whatever gain we have here, it will start to roll down because of all the parasitic capacitances which are there here, and it will cause a pole. So there are two poles here in this circuitry, and that's what we're going to calculate. The first one being at the output. So we're going to look at the output pole. So let's look at the output. Okay, we have these two devices. So what are the different capacitances that we have? We have CL, we have gate to drain of this device, drain to bulk of this device. For a device we have drain to bulk, and again gate to drain. And this point is actually the impedance looking as 1 over GM, because it's a diode connected device. So we will assume 1 over GM is small. So this point being AC ground, almost this is AC ground. Okay, just to simplify it. So you have these 4 capacitors plus 1, 5 capacitors. So this is the total C out. You add all of them. That is the total capacitance at this point. Okay. What is the R out? R out is the total resistance, which is the parallel combination of RDS6 and RDS2. Right. That is the total resistance that you see at that point. Now if you do minus 1 by R out C out, that's the RC product, which is going to give you the pole. R being the total R and C being the total C, you get the first pole. And that is in this particular configuration, assuming that CL is big, that's going to actually form us the dominant pole, or the smallest pole. Okay, so that is the first pole we calculated using the simple RC. Find the total R, find the total C. The second pole, as we said, we will encounter is, since this is an input, you will hop from this input to this node, and then hop from there to the output. Output pole P1 we already calculated. P2 is what we need to calculate now. And again here we are going to apply the same principle. This is going to be a pole caused by RC product. What is the total R and what is the total C? The total R at this point, which I'm calling as say R2 for this pole 2, it's roughly 1 over GM. This is a mistake. This should not be GM2, this should be GM5. Okay, so please correct this. I already scanned it. I don't know how to correct it, but this should be GM5 because we are looking at the GM of this device. Okay, so that is the total rough impedance there. I mean the resistance there. Now what is the total capacitance? What are the capacitance we're going to look at? We are actually going to look at a lot of capacitor if we consider this node. Let's see. Let's start with the biggest capacitors. CGS is always the biggest capacitor of all the capacitors. So we're going to see CGS of this device and the total CGS of this device. So those two come first, and they are going to be the dominant of all these other capacitors here. Then what else we will see? We will see drain to bulk of this device. For this device we'll see drain to bulk and gate to drain also, because when you are finding the total capacitance, remember there is no input. We make the input as 0 when we are trying to find a pole. Okay, so this point becomes AC ground, so these two gets added. Similarly for this device, this will get added here. And what happens to CL? Well, we are assuming that CL is big enough where by the time this pole happens, CL now acts as a short. So if it acts as a short, this point will become more like an AC ground or low impedance. So CGD6 will also add up. So we add all these capacitors. This becomes the total capacitor, this becomes the total resistor, which should be 1 over GM5. So what is the pole? The pole will be minus GM5 again. This is a mistake, by C2, C2 being the total capacitance here. So that will give you the second pole. So from input to output, as you hop, there are 2 nodes you hop through. So there are 2 poles, and we have calculated those 2 poles. Now this also has 0. Okay, the reason it has zeros is because you are hopping. Let's say when you hop from this device, there are two parallel paths the signal is going. It is going through the CGD and it's also going GM times VGS, right? So anytime you have two paths combining, you will get a zero. They two could add up to give you a zero at the output. In this case, let's just look at the zero here, which will be the same as before. As I mentioned, it will come out as GM divided by CGD. GM by CGD2 will become the zero, and previously I made a mistake of putting a minus sign here. This is not minus, it should be a plus sign, because this actually forms a right half plane zero, and right half plane zeros actually cause problems. Zeros are good as long as they're on the left half of S plane, but if which is with a minus sign. But if it just comes with a plus sign like it is, which is the right half plane, then they actually cause a problem, and we will see that more when we look into op amps and compensation part of it. Not now. We'll look into it at that time, that how it actually causes a problem. Okay, so this causes a zero. So we have found two poles and a zero. Let us assume again here, these are all dependent on, the pole locations are dependent on what are all these parameter values, right? But I'm going to assume that CL is the biggest capacitor, so this becomes the dominant pole. Dominant pole means the very first one to hit here. So I've got P1 as the lowest frequency pole or dominant pole. So the gain is pretty high, as we found out. This is the DC gain, and at this pole location, it starts to roll off. It's rolled off 3 dB here. Then it will start rolling down at 20 dBs per decade. Then we have the P2 and we also have the 0. We don't know which one is bigger, but I will assume again here is that since CGS's values are actually bigger than CGD, those CGS terms adding with CGD will actually be much bigger than this CGD here. Okay, so if this value is bigger, that means the pole is smaller. So we will have P2 happen before the 0. That is my assumption again here, and in most cases it is true. So P1, it was going down as 20 dBs per decade slope, negative slope. Then at this point it actually starts falling sharper. Now my drawing looks like as if it's going straight, but at this point it will change to 40 dBs per decade slope. Even though the plot doesn't look like this, but it will change it and it will start going sharper. Then at some point it will hit the 0 that we calculated, where again it will tend to move it up, right? By up it means it moves up the slope. So if it was minus 40 dBs per decade here, now it becomes minus 20 dBs per decade, and this becomes the Bode plot of the voltage gain, or this is how the voltage gain for this amplifier, okay, will change over frequency based on whatever these pole and 0 locations are. So we have solved this amplifier now to find what is the DC gain and what are the approximate pole and 0 locations. Okay, and what does the Bode plot looks like. So hopefully now you have seen a few examples of amplifiers, and you can extend this thing to other circuits that you have in the textbooks. Again, I would like to stress that please do the derivations of the complete small signal model to understand it, and these intuitive techniques that I'm trying to show you here, they give you 90% accuracy results. They won't give you 100% accurate results, because for that you have to do those derivations. But after you do those derivations, do not get lost in how to interpret them. Having this parallel intuitive way of deriving will help you understand that what those big formulas, the end of a derivation, you have a big formula, what does it mean, how to interpret it, where are the poles and zeros, what's happening at low frequency, what's happening at high frequency. Hopefully this approach will help you, show that both these techniques are identical and gives you almost similar results.